Hello, my dear students. Welcome to BYJU'S Exam Prep. This is MN Ramesh. Welcome to the session. Welcome to the marathon session, which we have started recently to help the students to revise the topics in the last few days. And this is going to be very, very useful for all the students, those who are going to appear for GATE 2023 in the first week of February. And we are here. BYJU'S Exam Prep is here to revise the concepts for those who want to quickly revise. If you have already completed your preparation, yes, this is a session is going to help you in revising the concepts, all the concepts of this subject, analog circuits. Already yesterday, Sanjay Rathi sir has taken part 1 of these analog circuits, and this session I am going to continue with the rest of the topics what Sanjay sir is not yet covered. So this is part 2 of analog circuits, which is common to both EC and electrical students, even IN students also, instrumentation students also. So guys, the first thing I want to request you guys is to refer and forward it to all our students, your friends in your social media groups, WhatsApp, Telegram, etc, etc. Please inform all the students to come and join so that everyone will get benefited. It is for all the students and it is open, it is free. It is on our YouTube channel, EC Electrical IN channel, and it is free for all the students. We are here to help all the students, irrespective of whether students are joined the coaching or not joined the coaching, self-prepared, everyone it is free. So it is really going to be helpful, all of you guys. Good evening, everyone. Raghuram, Pramit Banerjee, Navneet, good evening, everyone, and Satya Shri. Welcome guys, welcome to the session. Hope you all enjoy this session. I promise and I'll try my best not to bore you and to give you the valuable content in this entire 4 hours of session. So come on guys, keep increasing the numbers. Great guys, good evening everyone, good evening. Raghuram, Krishnaveni, Navneet, Raviteja, L435, Manoj Kumar. What is L435? Is it your roll number or what? Raghuram, yeah, daba ke like maro. Yes, that is mandatory. All of you have to like it and share it to other students. It is for you, your community guys. It is like other students also to know about this session. It is better if you can like it so that every student watching or searching for this content will get benefited. So that's what our intention and your intention also. You also can help. See, we are helping the students by giving the content free of cost. And you guys have to help the students or other students by forwarding it or by liking it or by sharing it, by commenting on it. So that helps Google algorithm or YouTube algorithm to come in the search when students are looking for such content. So it's not for us. Liking, sharing is not for us, for other students to get benefited. Pramit Banerjee, yes, I teach MOSFET, I teach entire analog circuits, I teach everything. But you know, Sanjay sir is also there, I am also there. So half part Sanjay sir is taking, half part I am taking, so that you will also get both the flavors of teaching. Everyone is having their own way of teaching and method of explanation. Their own examples. So here is the golden opportunity for you to get benefited from both of us. So Sanjay sir and me are sharing this because time is limited, so we are sharing this. Good evening everyone, good evening guys, once again. Yeah, going forward, this is about myself in brief. Did my ME from Usmania University, Hyderabad. I belong to Hyderabad, but still I'm taking this from the studio in Delhi NCR. More than a lakh students got benefited and trained under me across India, pan-India. And my areas of interest are analog circuits and electronic devices. These are my favorite subjects to teach. Of course, I can teach other subjects as well, but these are my command areas and where I get most satisfaction and most justification to the students. Yes, who is this? Navneet is asking what topics. Yes, I'm coming to that, guys. Topics also, I'll show you what are the topics I am going to teach in this 4 hours session. I'm going to list you that. But before that, just to remind you, just to make you aware that we have started this Maha marathon session every day 10 a.m. and 4 p.m. and we all, for all EC, electrical, instrumentation and computer science students can get benefited out of this. So subscribe to channel, you will get notification about each and every class. Okay. So in just 12 days, you will be getting complete revision. That is the beauty of this marathon session. And last year also, before last year also, many students really got benefited out of this. And this year you are going to be benefited. And we expect very good ranks from all of you guys so that you also will be happy. And we want your feedback. And we want your feedback after the GATE result. If you really get benefited, come and give us the positive feedback. If you don't get benefited, then please tell us what you want. We will give you that. So that helps you at least for next year and for other students as well. Apart from this, there is a workshop going on 15th January. This is to understand how you have to crack the GATE exam from Abhinav Negi, who himself is a ranker and a faculty with more than 11 years of experience, and he is going to show you the 7 success mantras to begin and to achieve the GATE rank. That is what, if you want to know about it, please attend the workshop at 12:30 p.m. only on our app, on BYJU'S Exam Prep app. If you have already attempted, well and good. If not, you please forward it to other students, maybe to your juniors who are in second year, who are in third year, who are in final year, or who is going to write the exam in 2024. It is helpful for them. It's not for 2023 students. It is for 24 students. What is this session? Marathon session is for 23 students, those who are going to write the exam in February, guys. And if any student looking for financial assistance as well, so BEP is there, BYJU'S Exam Prep is there to help you to support financially also. For that, what you have to do? You have to register for the scholarship test, which is going to be conducted on 8th January, 12 p.m. So you can get up to 90% scholarships. Many students already got benefited and you will be all of them. You can also be one of them. If you are looking for again 2024, because 23 is already almost over. Navneet is asking, Navneet, or who is asking for PDF? Sai Kishore asking for PDF. Yes, guys, if you want the PDF of this class, definitely we'll provide. Nothing is confidential here. Hi sir, I saw your Hyderabad coaching center. I am from IIT Basar. A great AK183. Great to see you back again online. So I am there offline, I am there online. So if you are getting benefited online, so that's the power of online classes. You know, you can watch classes anywhere from anywhere in India. Navneet, revolution in study. Yes, technology we have to keep using. Yes, coming to the straightforward the point, guys, the topics. Someone has asked that what are the topics I am going to discuss. In fact, analog circuits is a huge subject, big subject. But as per the concept, as per the requirement of this need of the hour, we are going to finish it faster. That doesn't mean that I don't teach everything. I'll teach everything. I'll cover everything, but in a quicker way, assuming that you know the basics. Because to teach everything from scratch, it takes a lot of time. That is why we have started our preparation long a year back, or maybe 2 years back, or maybe some students started 6 months back. It takes time to learn everything from the scratch. But now it is a revision session. We are doing the revision session, right? So revision cannot be more than this much time. So we have to quickly revise, and we have to, as I told you in earlier sessions also, that you have to revise and you have to attempt mock tests, and you have to realize what is going well and what is not. So then you can correct it like that. So these are the topics I am going to cover quickly in next 4 hours. So yes, 4 hours is very less time, but assuming that you are already good in the basics and the topics, so I can cover entire things quickly so that you can all recollect what we discussed earlier or what you studied on your own. It is for both those students who attended my class, they can also recollect everything what they have studied and listen to my class. And those students who studied their own also recollect, because what we are teaching, after all, from the standard books what we have, right? So we also gone through the textbooks, and we added our content, or we explain you in a simplest way possible to understand and to represent again to reproduce again in the examination. So that all things you can recollect after watching this revision session. That's what the purpose of these guys, to revise everything. Okay, so let me change the color of this pen. I think it is not visible. Red color is not visible. So let me take blue. Yeah. So I'm going to teach diode circuits. So what these diode circuits? All the circuits having diode as a primary component will be a diode circuit, and we are going to see as per the GATE syllabus. I'm repeating, guys, this is for GATE syllabus. If anyone want to write other exams like ESC or some other ISRO or etc., we'll come up with another revision session as per that syllabus. Since GATE 2023 syllabus is to be covered, I'll be covering what are all the diode circuits there under the GATE syllabus, like for example clippers, clampers, rectifiers, regulators, voltage doublers, etc., etc. Okay. Another student, Kirtana, is saying multi-stage amplifier important for GATE. Not that very important it is. Sometimes there are some questions, but they are simple questions. Diode circuits are very important. Biasing is very important. It doesn't mean that you don't get questions from multi-stage. It may come, but the frequency, how many times a question has come from diode circuits or BJT, is more than multi-stage. But there are questions from multi-stage as well. So it doesn't mean that multi-stage don't have the questions. It is. But the probability of getting question from multi-stage compared to other topics may be lesser. Like for example, if I compare with op-amp, the probability of getting a question from op-amp in the next GATE exam is very high compared to the multi-stage. Because every time, if you see the history of the 20 years or 15 years, op-amp questions are plenty. Every year there will be 1 or 2 questions on op-amp. But whereas multi-stage, there are questions, but not every year. That is the difference. Okay. An electronic device in which the electric current flows in one direction only. Yeah, exactly. Poonam, you are saying something about diode, I think. Yes, electronic device. A diode is a device. A diode is a component where current is allowed only in one direction. That is the specialty of the diode. But here there is a small catch. I'm not going to discuss how diode works. Okay. That part comes under electronic devices. That is another subject for EC students. For electrical students, it is not required. For instrumentation students, maybe not it is required. But electronic students, it is a separate topic, separate subject is there. We'll discuss that separately in the upcoming sessions in the marathon as well. I'm going to give you the revision on electronic devices. There I'll discuss about how diode will function, how the construction operation, how the BJT will work. All those details we will discuss there. Okay, but what are we going to discuss here? We are going to discuss rectifiers, where rectifiers will have a diode as a main component. Of course, other than diode, there are other components like resistors, etc. will be involved, but the primary heart of the circuit is a diode. Such circuits I call it as diode circuits. Similarly, regulators, I can say clippers, clampers, etc., etc. Okay. So these are the circuits I am going to discuss, how they work and what are the important points to remember. Mostly I highlight and emphasize on the important points, because studying about basics of these circuits, okay, it is required to refresh, but what to focus and where to focus more also I am going to give you. Is it visible, guys? My screen is visible for you and this color is fine for you to write, because it's a dark background. I am writing with the light blue. Is it clearly visible for you? If yes, please comment on this. Yes, Raghuram, yes, in the rectifier circuits, again, yes, there are types of rectifiers: full wave rectifier, half wave rectifier, bridge rectifier, etc., etc. are going to be discussed. Okay, then we'll move on to BJT biasing, how BJT is to be biased and what are the important points to focus on biasing, and how the amplifiers, BJT amplifiers especially, and how the analysis of amplifiers, what type of questions will come in the examination in the amplifiers. It's going to be important, guys. BJT amplifiers, there are many questions in the previous exam as well. So you have to understand how amplifier works, how to analyze, and how to answer the gate questions and what type of questions will come in the gate exam. Those are all things we need to study. Let's study all those things. Let me revise all those things. Then the types of amplifiers, in fact, feedback amplifiers, power amplifiers, multi-stage amplifiers, these are all types of amplifiers, but fortunately power amplifiers is not there in the gate syllabus. That's why I'm not going to give you power amplifiers. If you target for other competitive exams, maybe power amplifier is required. For gate, it is not required. From couple of years onwards, there is no questions, or in syllabus also it is not mentioned power amplifier is there. So power amplifier is not there. So feedback amplifiers I'm going to tell you, and the important points, topics. Similarly, multi-stage amplifiers I'm going to tell you how multi-stage, why multi-stage, what to focus on multi-stage, like Cascode, Darlington, very, very important, Cascode and Darlington. If at all any question, mostly, as I told you, this is not that important, but if at all it is, any question is coming, mostly it will be asked around Cascode and Darlington. So you have to have idea about Cascode and Darlington. So that also I am going to tell you. Okay. Chinmay Rai, good afternoon. How are you? Are you ready, guys? Shall we move ahead to understand these topics in a very quick time? Are you all guys ready? And are you sharing this to other students? Yes, please put it in different groups you will be having. I know you are all very active in social media groups. Whenever you receive a WhatsApp message, Telegram message, Instagram, Facebook, etc., etc., you all get alert. You will become very active, na? Similarly, you please send this link to other students. There is a share option in the YouTube view when you are saying. So please copy that and share it to all other students. Let's reach it out to the maximum number of students. Our intention is only to reach to maximum number of students, right? Ready, guys? Let's move on to the first topic of today's class, that is clippers. So the first topic I am starting is clippers. As you know, the clipper, the definition is here clearly written. Clipper is a circuit. You must be already knowing what is a clipper. The name itself tells you what is a clipper. Clips. Clipping is nothing but removing, cutting. So clipper is a circuit which can, it is a circuit. When you pass a waveform through that circuit, then the part of waveform can be removed. Which part? Any part where you wanted. Above certain level, or complete positive half cycle, complete negative half cycle, or only between these two, or only above and below certain levels. Any part of the waveform can be clipped using a circuit called clipper. That is the clipper. The name itself tells. It is also called as slicer. It is also called as a chopper. Chopping, slicing, all same meaning it is, right? So clipper is a circuit which limiting, chopping, cutting, clipping. So all are same meaning, right? So clipper is a circuit which clips or removes, limits, prevents some portion of the input waveform above or below a certain level. This all can be decided by us designing the circuit properly. Where you want to clip, you should be able to do that. That is what an engineer job is. You will be designing a circuit. Suppose if I am a customer, and you are an engineer, I will ask you that, sir, I want this waveform to be clipped at this level or clipped at this level. Then it is your job to design that circuit, right? And using what? Obviously diodes. Okay. So there are different methods to clip that waveform. That is what we call it as types of clippers. You can see here. So we have shunt clipper, series clipper, bias clipper, double clipper, bias double clipper. These are different methods of designing a clipping circuit, right? Now what is shunt clipper? As the name tells you, what is shunt clipper, what is series clipper, what is bias clipper, double bias clipper? Can you guys comment what you know on this, so that I'll also get an idea to what extent I should revise or what extent I can go deeper. Can you guys tell me what is shunt clipper, series clipper, what are the differences here? Bias clipper. The name itself tells you the bias clipper is nothing but a clipper having some DC involved in it, a battery connected. So bias circuit above that level, suppose biasing is nothing but some DC voltage, right? Suppose if I connect a 2 volts battery in the clipping circuit, so that circuit may clip above that level or below that level. So such circuits called as bias clippers. Come on guys, comment what is series clipper, shunt clipper. It all depending on the name is given depending on what? Depending on how the position of the diode is. If the diode is in shunt with the input signal and you are taking the output across the diode, such circuits are called as shunt clippers. As simple as that. If the diode is in series with the input, you are applying the input directly to the diode and taking the output from the diode. Okay, not across the diode. It is in series with the input. Such clippers called as series clippers. As I told you, bias clipper is nothing but having a battery in it. Double clipper is nothing but clipping at two levels. Double means two, right? Clipping at two levels is double clipper. Obviously, double clippers will have two diodes, isn't it? One diode clips at one level. So if you want double clipper, obviously you need two diodes. So such clippers are called as double clippers. And then bias double clippers, having two diodes to have two levels of clipping, but at what level can be decided by having a battery in it. This is what double clipper with biasing. Okay, these are just types. Shall I go to explanation of one shunt clipper here? See guys, this is a shunt clipper. You must be aware already. Yes guys, you know what is the other name where we are already calling it as a clipper. No, it's already called as a clipper. Can anyone say what clipper it is? Is it clipping above a certain level or below a certain level? Because there is no battery involved anywhere. So we can call it as simply a clipper which clips above zero level or below zero level, isn't it? So tell me, is it a positive clipper or negative clipper? Clips above zero level or below zero level? Come on guys. Yeah, Ratan is saying below. Yeah, negative clipper. So negative clipper means negative half cycle is clipped off, right? Come on guys, name this clipper how it is. Whether we called it as shunt clipper. Why we call it as shunt clipper? Because the diode, you see, the diode is in shunt with input and output. Okay, it is parallel to the input and output. That's why it is called shunt clipper. But what it is clipping, based on that we can give another name. Negative clipper or negative half cycle is clipped off or positive. So this input here guys can be anything. It can be a sinusoidal signal. So general opinion among the students is that the input is a sinusoidal always. No, not necessarily. It can be any signal. It can be a triangular, it can be random, it can be square, any signal. Any signal it can be. Just for understanding, just for explanation purpose, we may take it as sinusoidal signal. We can understand the same working or the same behavior can be for any other signals applied. So only for understanding we go for sinusoidal. Remember this. It's not that always input for a clipper is sinusoidal. It can be any signal. Now if I go for a sinusoidal signal, some part of the signal is above zero, some part of the signal is below zero. Again it is positive above zero and it is negative below zero. It repeats. That's what is called as cycles. One cycle and second cycle, etc., etc. So we want to understand what's going to be the output here. So for that what? We need to understand how the diode is behaving as. How diode behaves? Either it will be forward bias or it will be reverse bias. There is no other option for the diode to be. Whenever you have a diode, the circuit is going to be very simple guys. Just blindly you can think that if you have a diode, any circuit, let it be clipper, clamper, rectifier, any circuit it is, if you find a diode, it will be either forward bias or reverse bias. Based on what? Based on anode voltage or cathode voltage. Voltage at anode compared to the cathode voltage. If anode voltage is higher than the cathode voltage, the diode is said to be forward bias. If not, it is reverse bias. If not, it is reverse bias. So just if you know what is forward bias, reverse bias is obvious. Exactly. Raghuram, this is what you have to remember. Many students will remember like anode voltage is greater than 0 or anode voltage is positive, cathode voltage is negative, is called as forward bias. Not necessarily. Always not necessary. Even cathode is positive. If anode is more positive, then the diode is said to be forward bias. So always remember, anode of the diode, to be forward bias, anode of the diode should be higher than the cathode. Always remember that, isn't it? Right. Now let us examine what this diode is, because you know what is this sinusoidal signal is. Input is sometimes positive with respect to this or sometimes negative with respect to this. It can be negative with respect to this because it is changing the cycles. Then you can decide. The diode also can change its region of operation. It can be forward bias or reverse bias. Okay, let's understand the case 1 as if anode voltage, the voltage here is greater than 0. Why? Because cathode is already at ground. Cathode is already at ground. So if anode voltage is greater than 0, when it becomes during the positive half cycle, right? For positive half cycle of the input. For positive half cycle of the input, anode voltage becomes more than the cathode voltage, which is more than 0. Then what happens to diode? Then diode is forward bias. Once the diode is forward bias, how the diode behaves like? Once the diode is forward bias, it behaves like short circuit. Assuming an ideal diode, the diode is like a short circuit here. So diode is forward bias, that is nothing but behaving like a short circuit. Ideally, diode when it is under forward bias is like a short circuit, that all you know. So please don't ask me how it is short circuit, because that can be proved. That can be proved by finding the resistance offered by the diode under forward bias. But that cannot be done now. That has to be done later. Okay? That can be done later. In another subject, as I told you. Okay? Now, it is short circuit. Then, what is output is our question, right? Output voltage, VO, is what? Where you are taking the output? Output is across the diode and the diode is short. So, how much is output? 0. Output is 0. So, whenever input is greater than 0, whenever this waveform is greater than 0, output is 0. Okay? Output is 0. Similarly, second point, input may not be always greater than 0, right? Sometimes it is going negative also. So whenever input is negative, here it is negative, then anode voltage is also going to be negative. Cathode is already at 0. So when input voltage or anode voltage is less than 0, that means for negative half cycle, what happens to the diode? Come on guys, what happens to the diode? Same circuit. Circuit is same. Here it was the diode only again. It is the diode only, but the diode anode is now negative, cathode is 0. So what happens to this diode? This diode is like reverse bias. It is like reverse bias. It behaves like open circuit like this. Diode is reverse bias. It is like open circuit. Hope you guys all these things know, right? Shall I go a little faster if you know? I don't want to make you bored about this. Or if you have any questions now, please stop me and ask me. Keep asking me the questions so that I'll give you more and more content. More the questions you ask, more the deeper the content, and exactly what you want I will know. Right guys, great. So diode is reverse bias. The moment diode is reverse bias, the current flowing through the diode is 0. That means the drop across this is 0. No current is flowing. So when drop is 0, the voltage here, whatever is there, the voltage here is exactly same as this voltage, which is nothing but V0. What is this voltage here? Negative half cycle. So the voltage here is also negative half cycle. So V naught is same as Vi, which is negative half cycle, because we are talking about negative half cycle, same as input. So what happened? Whenever input is positive half cycle, output is 0. Whenever input is negative half cycle, output is same as negative half cycle. So what is clipped off? Positive half cycles are clipped off. So that's why this is called as positive clipper. This is called as positive clipper because positive waveforms got clipped off. Negative waveforms are passed. Acha, Navneet is asking more questions. Yes, there are questions there. So I'll be showing the questions because it is a revision session now, Navneet. So we have to first quickly revise the topics and then the questions also. Yes, I have good number of questions as well. For every topic I have questions. Topic wise I have segregated. Change the pen color. Okay. Shall I go for yellow color? Otherwise, I think yellow will look better. Yellow looks better, I guess. Right? So this is the waveform, guys. So this is the input waveform. This yellow color is the input waveform Vi. But what is the output waveform? Output waveform you got is positive half cycles is 0 like this. Negative half cycle is same as like this. Because that's what we understood, right? And again positive half cycle 0. Negative half cycle same like this. So this blue color is output waveform. Done. Since this positive waveforms got clipped off, it is a clipper. It is a clipper called. Done. Same way. Yeah, sometimes one more point is also required to draw the transfer characteristics. Let me explain what is transfer. Sometimes you people require this. This is transfer characteristics graph. This is the graph between VO and Vi. Transfer characteristics we call it as. Okay. So for that you need this. When VO is 0, you have to find what is the slope. Slope is 0, obvious, right? Here from this waveform, we can say, from this equation, we can say slope is 1. Slope is simply nothing but coefficient of Vi or V naught by Vi. Here slope is 0 because coefficient of Vi is 0. Here slope is 1 because coefficient of Vi is 1. So that we need to plot here. When Vi is greater than 0, what is the slope we got? 0. So that is what you need to plot. That is what we need to plot here. See, this is slope equal to 0. Done. When Vi is less than 0, that means this side the slope is 1. So this is what slope is 1. This is called transfer characteristics graph. It is important, guys. Transfer characteristics graph is important. Gate point of view if you see. So this is the waveform if you want to plot. I already plotted and shown this waveform. This is how the input waveform is, and this waveform will not come, this waveform will not come, but this will come and this will come. That's why it's called as positive clipper. Already we have seen this, right? Any questions so far, guys? Any questions so far? So that if you know this, rest of the circuits are going to be very simple. I am going to give you a shortcut for this or a trick for this to help you in the further circuits, complicated circuits also. Are you ready for this? Have you understood or not? First thing. Any questions from this? Transfer characteristics, Raghuram once more. Okay, sure. Raghuram, transfer characteristics is the graph between VO and Vi. Okay. Ratio of VO and Vi. So it's nothing but slope. So from these equations of output, we need to find the slopes first. From this and from this. These two equations, we need to find the slopes. And we just need to represent the slopes there. How to find the slope? it is nothing but VO by VI. Here it is 0, that's why it is 0. VO by VI is 1 here, that's why slope is 1 here. So we just need to find the slope and then put it in the graph. When VI value is great, this is 0, right? From here it is 0, this side is positive, this side is negative. Similarly, V0 is positive here, VO is negative here. So when VI is positive, greater than 0, how much is the slope we got? Slope we got 0. That's what I have shown here. Slope is 0. This line, yellow color line, is slope equal to 0. This line, when VI is negative, is slope equal to 1. Just like that. Whatever the slope you got, you have to plot there. Suppose if you get a slope equal to half, then you have to represent like that. Accordingly, you have to represent. If slope equal to 1, like this. If slope equal to 3 by 4, you have to represent like that. Remember. And one more very important. Slope in any clipper circuit, is always lesser than or equal to 1 only. Slope will never be greater than 1. Slope will never be greater than 1. Clear now? Can you guys tell me in clippers? In clippers, slope will never be greater than 1. In clippers, slope will never be greater than 1. Can anybody say why? Can anybody say why slope will never be greater than 1 in clippers? Suppose when you are solving any clipper circuit, sometime, somewhere, if you find slope is greater than 1, that means something is wrong. Something is wrong in your calculation. You have to recheck the things. Clear? Check it, guys. Exactly, Raviteja. Clipper circuit, we are talking about clipper. Clipper is something clipping off. That means output is less than input. What is after all slope? VO by VI it is, right? Output is less than input. So its value is definitely less than 1 always. If VO is greater than input, output is greater than input, that's not called as a clipper. Okay, it's called as something else. Need not be amplifier, it can be called as something else. Perfect, guys. You guys are rocking. Now I'll give you a technique or trick. Are you ready? Won't slope come in Kirtana? Good question. Kirtana is asking, why can't the slope be here? Right? Here. This is also slope equal to 1. That is a good question. Reason is, you see guys, slope equal to 1, here, slope equal to 1 when you got V0 equal to Vi. What is V0? Negative, right? Because Vi is negative. V0 is negative, Vi is also negative. If you see this graph, this is minus V0, this is minus Vi. Both are negative. That's why ratio is 1, not negative 1. But if you see this, slope is minus 1 here. Isn't it? V0 is positive, Vi is negative. So the ratio is negative. But our slope is 1, not negative. That's why this cannot be the graph, this can only be the graph. Kirtana, did I answer your question? Perfect. Now, let me tell you a trick. Very beautiful trick, guys. It helps you in a lot of situations. Check this, especially in clipper circuits. This trick I am going to tell you helps you in most of the times in clippers. Okay. So let me erase all this stuff here. Check it here. What we call this clipper as? We call this clipper as positive clipper, right? That means positive waveforms are clipped off. Remember, all of you, see the direction of the diode, pointing of diode. Diode is pointing towards ground. Diode is pointing towards ground. Okay? That means above a certain level will be clipped off. Remember this. Above a certain level is clipped off. When diode is pointing down like this. Above a certain level. What is that certain level is? See where this cathode is connected to? Cathode is connected to the ground, right? That means 0 volts. So that certain level is 0 volts. So by seeing this circuit, I will say diode is pointing down and cathode is connected to 0 volts. So above 0 will be clipped off. That's what positive clipper means. Above 0 means positive clipper. Is this nice? Now I'll tell you. Now I'll tell you one more thing. Suppose diode, no, why to tell you? I'll show you the circuit. Now you tell me this. Now you tell me, don't do anything, just tell me diode is pointing upwards. When diode is pointing downwards, above certain level is clipped off. Now below certain level is clipped off. So it must be a negative clipper. It must be a negative clipper. You can verify, guys. It must be a negative clipper. But what is that certain level? Since anode is connected to the ground, 0. Below 0 is clipped off. Below 0 is clipped off. Is it clear? I called it as negative clipper because anode is connected to 0, below 0 is clipped off. Earlier circuit, this circuit, since diode is pointing down and the cathode is connected to ground and above 0 is clipped off. Positive clipper and negative clipper. Isn't it simple? Isn't it simple, guys? Now I'll show you one more thing. Very simple and useful, guys. Very simple and useful. Now without doing anything, you can say this. You can say these things now without doing anything. Now see. Suppose if I put a battery here. Let's say of 2 volts. Now I call this as biased shunt clipper. It is called as biased shunt clipper. Shunt series doesn't matter, biased clipper it is. Now don't do anything. Don't do any calculation like this. Don't find anything. Just tell me where the clipping happens. By seeing the circuit, just tell me where the clipping happens. Come on, guys, where the clipping happens. Where the clipping happens. Come on, this is the trick you have to know. This type of tricks only helps you. In this very short time, suppose if you have not prepared analog circuits, you have not prepared clippers also, this trick definitely helps you in just finding the answers few seconds. Come on, make it faster. Where the clipping happens. That's simple, very good. Come on, guys, rest of the students. Where are you, rest of the students? Diode is pointing down, right? Diode is pointing down, as I told you. So clipping must happen above certain level. Where is that certain level? Since cathode is connected to 2 volts battery, above 2 volts is clipped off. If you don't trust me, you just solve this circuit and like this you solve this and check it. The same is going to happen. If you want the waveform to see, how the waveform to see, I'll show you the waveform as well. If this is the clipper, how the waveform is. Let me show you that also. Okay, let's say this is the input signal. And let's say this is somewhere 2 volts level. This is 2 volts level. Right, 2 volts battery is there. Now what is clipped off? Above 2 volts is clipped off. So how the waveform is? I'll show you the waveform with this black color. This is the waveform coming. No need to calculate anything, just by seeing the circuit, by seeing the diode position, you can directly say. So this part of the waveform which is here, gone. This is clipped off. Above 2 levels is clipped off. Clear? Now can you plot any waveform directly? Yes or no? Remember, guys, positive part is clipped off above 2 volts. Raghuram, perfect. Does this clear trick is helping you, guys? Must needed, guys. This type of tricks are must needed. Remember, must needed. Is it helping you? Yes? Bilkul. Very good. Chalo. Let's show you another circuit. So from now onwards, I'll try to revolve around these tricks and shortcuts, because this is the time for that. If I started teaching 8 months back or 1 year back, I'll go and teach in this way. But this is also important, guys. Now, without knowing the concepts, shortcuts may sometimes confuse you. So both is required. So if you don't have time at this point of time, then just go for the technique. That's sufficient. Now I don't need to do. If I want to do this also, you can do this, guys. It's okay. Vi greater than 0, diode is reverse bias. That is like open circuit. When diode is open circuit, V0 is same as Vi. In that case, slope is 1, because slopes are also required to plot the transfer characteristics. So when Vi is less than 0, what happens? Diode is forward bias. Then it is short circuit. Then V0 is, when it is short circuit, is like 0 volts across it. So it is 0 volts. So in that, slope is 0. Done. Output is 0 whenever input is less than 0. So negative part is clipped off. So it's called negative clipper. That's what already we said without seeing all these calculations, right? So don't waste your time. If you see this type of circuit, directly go for it. Go to the third one. Yeah, series clipper. Doesn't matter whether it is shunt or series. Only difference is series clipper, why it is called as, because this diode is in series with the input like this, right? Diode is in series like this. Here also, if you want a shortcut, you can do that shortcut also. So first let me explain this very quickly, and then I'll give you a shortcut, because to give the shortcut, first I need to justify whether it is working properly, what type of clipper or not. Is it positive clipper or negative clipper, we can see here. So the concept remains same. Let's go for case 1. So let's say case 1 is Vi greater than 0, because input can be greater than 0 or less than 0, whatever the shape of the input is. So I am not constrained to only sinusoidal signal. It can be anything. That's why I am calling it a Vi. It can be triangular, it can be random, it can be ramp, anything it is. If it is greater than 0, how the diode is going to be? Diode is going to be forward bias. It is like short circuit. Once it is short circuit, it is like this, shorted. Then this is VO and this is Vi. So what is VO and Vi? They are same. They are in the same line. So V0 is equal to Vi. So slope equal to 1. Why I am finding slope is just to draw the transfer characteristics. The second one is, if not Vi greater than 0, it must be less than 0 it is. Then diode is reverse bias. If it is reverse bias, it is open circuit. Isn't it? It is open circuit. If it is open circuit, it is behaving like this. It is open. So no current flows, no voltage drop. So output voltage is 0. In that case, slope is 0. Done. So if you want to plot the waveform and transfer characteristics, you can. Vi greater than 0. What you got? Slope equal to 1. So plot it. Vi greater than 0, slope equal to 1. Vi less than 0, slope equal to 0. That's it. So waveform. So same it is, similar it is. Vi greater than 0. So same as input. So let me change the plot here, color here, same as input. Less than 0, 0. Positive, 0, positive, 0. So this part is gone. So what it is? Negative clipper. Negative clipper. So in the same way, you can check that if the diode is in this direction, if this diode is in this direction, you can say that it is negative clipper. If it is in other direction, it is positive clipper. This is a negative clipper. Then if I go for this circuit, this must be positive clipper. Agree? This must be positive clipper then, right? Agree or not? Perfect. Because just diode direction is reverse. Here I have not added the battery. If it is added, according to that, above 2 volts or below 2 volts, etc. Done. Now is this one. I don't want to explain this. Now you have to tell me. Already you must know this. This is called bias clipper. I don't want to explain this now. You have to tell me. Come on guys, you have to tell me this. What type of clipper it is? Tell me faster what type of clipper it is. Diode direction is towards the bottom. Diode direction is this way. Diode is in this way. So how this clipper can be called as? When diode is pointing down like this, it is called as negative clipper we called already, isn't it? Negative clipper or positive clipper? Positive clipper, not negative clipper. It is positive clipper. When diode is pointing down, it is positive clipper. Negative clipper or positive clipper? It is positive clipper guys, not negative clipper. It is clipping the positive waveform, right? Positive clipper. But clipping what? Clipping above 10 volts because cathode is connected to 10 volts battery. So how the waveform is expected for this? How the waveform is expected? If this is the input waveform and let's say this is somewhere 10 volts, above 10 volts is clipped off. So below 10 volts is available. So this type of waveform is expected. Isn't it simple? So don't go for entire calculation and waste of your time. Okay, don't do such calculations when you confirmly know this, because that unnecessarily wastes your time. Suppose if you find this question in the gate examination, you should find the options for this type of waveform, the red color one. You should not waste your time finding what happens when VA equal to greater than 0, what happens when VA, don't waste your time. So directly you have to go. Move on to the next one. This one guys, double clipper I call it as. It is called as double clipper. Tell me. Why it is called double clipper? Because two diodes are there. This is one diode, this is another diode. But remember, two batteries are also there. That means it is bias double clipper. Otherwise, double bias double clipper you can call it a. But no need to call it a double bias because double bias means two batteries. If there are batteries, you call it as biased only. Come on. With the technique we can see directly we can get the answer. With the technique I told you. With the technique I told you, you can get the answer directly. See all of you. This diode is pointing towards down. So what it will do? It will clip above part. Above what? Above 5 volts. So this diode, it is exactly like bias clipper what we discussed, isn't it? It is pointing down, connected to 5 volts. So above 5 volts is gone. Above 5 volts will not come. So below 5 volts it retain. But what is this diode? Pointing up. Pointing up, that means what? It clips below certain level. What is that certain level? 5 volts. What 5 volts it is? Negative 5 volts. See, it is minus and this is plus. So I'll say this is the waveform. Okay. And let us say this is plus 5 volts. And another battery is minus 5 volts. Somewhere here it is minus 5 volts. Now you have to tell me. This is 5 volts, right? This is minus 5 volts. Now you have to tell me where the clipping happens. This is clipping above 5 volts. So above 5 volts is gone. This part is gone. and this is clipping below certain level. What is this certain level? Minus 5 volts. So minus 5 volts, below minus 5 is gone. Right, this is gone. So what is remaining? Remaining is only this. Isn't it? Input portion between 5 and minus 5, Ravi Teja, exactly correct. It clips above 5 and below minus 5. Exactly. It retains, it transmits the signal between 5 and minus 5. So this portion is at the output. This blue color is output. It is clipping above and below. Isn't it beautiful, guys? Simple and beautiful, isn't it? But remember, tricks are applicable not in every circuit. Wherever you have a diode like this and a battery connected like this, diode like this, battery connected like this, this is applicable. Suppose if you have a resistor connected like this, for example, this may not be applicable. I'll tell you that type of examples also in some numericals when we discuss. Not now. Okay? This you can say now. This you can say. Now you tell me, guys, this one. What is this one? You must say this. I don't want to explain this. You have to tell me. Yes, Payash Kumari. That's superb. If you are liking it, my purpose of standing here for an hour almost is survived. Come on, guys, you tell me this one. This also can be done without doing anything. You can directly say this. See this. This is pointing down and connected to 8 volts. Right? Pointing down and connected to 8 volts. So it clips above 8 volts. This diode clips above 8 volts. Above 8 volt signal will not come. And this diode is pointing opposite to this diode. That means it clips below what? Below 5 volts. So clips below 5 volts. What is this? Let me call this as D2. Let me call this as D1. So D2 and D1. D1 clips below 5 volts. D2 clips above 5 volts. So what is available? Between 5 and 8 is available. So how the waveform looks like? Let me show this time a triangular waveform like this. It can be any waveform as I told you. Okay. Now, let's say this is 5 volts level and 8 volts is somewhere here. This is 8 volts. Let's say I may be not exact to the scale, guys. Pardon me for that. Okay. This is 5 volts and 8 volts level. So where is the output available now? Between 5 and 8 it is available because above 8 is gone. Nowhere available. Between 5 and 8 is available. So this is what the red color one is, output. So below part all is gone and above part is all gone by D1 and D2 respectively. Perfect. Take some example like this. Now with this, you can do this as homework. Shall I give it as homework, guys? Shall I give it as homework to you? It is same circuit what we discussed. Okay. Diode is pointing down. So above certain level is clipped off. What is that certain level? Above VR. What is VR? VR is given 10 volts. So above 10 volts is clipped off. Below 10 is available, as simple as that. But here there is a small catch. Input is 20 sin omega t, that's the sinusoidal signal with peak value. 20 sin omega t means what? It is a sinusoidal signal like this with a peak value of 20 volts. That is the signal. So above 10 is gone. But here you have to remember, the forward resistance is not 0 and reverse resistance is infinite. That means RR is infinite, means it is like open circuit when it is under reverse bias. But forward resistance is not 0. Ideal diode will have RF is equal to 0, RR is equal to infinite, V gamma is equal to 0. But practically they are not. So the data given here is partially ideal, partially practical. So it doesn't matter if RF is given. When diode is under forward bias, you just need to consider it as like a resistance of what? 100 ohms. And calculate accordingly. So when diode is under forward bias, output is what? The voltage across these 100 ohms. Let's say the current flowing here is I. So I into 100 ohms plus the voltage VR plus VR will be the voltage. That's what output voltage. So actually expected is VR plus something is additionally coming because it is practical diode, not ideal diode, since RF is not 0. If you substitute RF is equal to 0 in this case, RF equal to 0, in place of 100 if you substitute 0, it is exactly like what we know. Apart from that, it is nothing new, it is similar to what we know. Okay? Any questions? Shall I move forward? Many more things we have to discuss, guys. Shall I move forward? Hope these tricks definitely help you. I'll tell you one more technique and one more important concept in clippers. That's why I want to move. This is the waveform to plot. So this is what 20 volts, right? Just I want to show you the answer also for this. 20 volts. So 10 volts is somewhere here. This is the reference voltage 10 volts given. Somewhere here is 10 volts. Now output asked is to find the waveform. So then how the output? Actually it should come like this if it is ideal diode. Above 10 volts is clipped off. So like this is the waveform expected, ideally speaking. But since it is practical diode, RF is there, na? RF, forward resistance RF is there. So the waveform would be something like this. And depending on RF, the value is different in fact. RF is 100 ohms. Suppose if RF is different value, the value what you are getting it here at the output here, this is additional because of RF only. That will be different. Okay, that can be done now. Now take this, guys. This is very important. Draw the transfer characteristics. If Vi is 50 sin omega t, this is 50 sin omega t. Sin omega t. This is D1 and let's call this as D2. Now tell me, one thing we can clearly say based on this diode is pointing down like this. This is a combination of series and shunt. This diode is pointing down. That means above certain level will be clipped off. But what level? Looks like 10 volts. Above 10 volts is clipped off, isn't it? But no, guys. Come on, this is very, very important problem. Very, very important concept I am going to tell you. Come on. Come on guys, tell me this. Shiva Shankar, very good. Exactly. It looks like this diode D2 gets forward bias. Looks like when anode voltage, let me call this as VA2, okay. VA2 is greater than 10 volts. And that is true. If this diode to become forward bias, the anode voltage here must be greater than 10 volts. That's true. Then only diode will become forward bias. But what is this anode voltage here? Which is nothing but the voltage here. The voltage here is, let me call it as Vx. Let me call it as some X voltage. That we need to find. If this diode is forward bias, or it can be reverse bias also, we don't know whether this diode is forward bias or reverse bias. Now find it. Suppose if this diode is reverse bias, that means it is open circuit, the voltage here is going to be 0. Vx is going to be 0. Vx is going to be 0 because this is connected to 0, nothing is coming here. Vx is going to be 0 when Vi is less than 0 or when D1 is reverse bias. Or I can say. But Vx becomes how much is the question when this diode is under forward bias. Suppose if this diode is forward bias, then when D1 is forward bias, if this diode is forward, because this is also a diode, it can be forward bias, it can be reverse bias. Exactly, Hemant Krishna, exactly. So if this diode is forward bias, the voltage here is nothing but voltage division is happening here. Whatever the input you are applying is getting dropped across this and dropped across this. That is the voltage which is called as Vi by 2. Whatever the Vi you apply, that is half only available here. Because it is getting distributed across these two resistors 10K and 10K. Since they are equal resistances, half is happening. Half voltage dropped here, half is dropped here of the input what we apply. If they are different values, obviously yes, different division happens. Now let's say here it is 12 volts applied. At the input if it is 12 volts. Because it is going up to 50 volts. Or let me start with not 12 volts, let me say, yeah, let's start with 12 volts, okay. That serves a purpose. Let's say it's 12 volts. Then how much is the voltage available? It's going to be 6 volts only, because half of that only available. If this is 6 volts, here is also 6 volts and cathode is at 10 volts. So this diode will become reverse bias only. Suppose here it is 18 volts. Then the voltage here is 9 volts only. Then what is the voltage here? 9 volts. 9 volts is not sufficient to make it forward bias. Still it is reverse bias. Suppose the voltage here is more than 20 volts. Input is more than 20 volts. Then the voltage here is more than 10 volts. Whatever it is, more than 20 means, let's say it is 21, 23, 25, 30, 40, 50, whatever. Then half of that is available here. So let's say it is 22 volts. Then here voltage is 11 volts. 11 volts is here and it is 0. So this diode now comes into forward bias. Once it is forward bias, short circuit. So output is 10 volts. Not 12 volts, 10 volts. Because once it is short, the voltage across this is this. So to make this diode forward bias, anode voltage should be greater than 10 volts. To get anode voltage greater than 10 volts, input voltage should be greater than 20 volts. Input voltage should be greater than 20 volts. Understood? So how the transfer characteristics? Is there any space here? Let me show you the transfer characteristics here. Let's say this is Vi, this is Vo. I'll show you the transfer characteristics now. Listen carefully here. Let's say it is 10 volts, let's say it is 20 volts. Less than 0, output is 0. So it is 0, right? Greater than 20, how much is the output voltage? It's going to be 10 volts. See, greater than 20, when input is, here the voltage is greater than 10, then makes this diode forward bias and the voltage is 10 volts like this. And between 10 and 20, this. So what is the slope here? Slope is 0.5 here, and slope is 1 here, slope is 0 here. You guys got it, guys? Equal resistance, it gets half of the input voltage. Correct. So this is what? And see, this is the portion from here to here where input is available half here at the output. Got it, guys? This is one of the nice problems we had to understand the effect of these two resistors. Okay? Clear? Any questions? Shall I make small modification and ask you a question then? Shall I make you a small modification? Slope 0, no sir, after 20. Sorry, yes guys. Sorry, this is 0, slope is 0, so not 1. It's a typo. Yeah, slope 0, yes. Horizontal line is slope 0, right. Kirtana, sorry. That's correct, slope 0. This is half. Slope 1 means somewhere here like this it has to come. That's correct. Okay? Shall I ask you a small modification in the question? See like this. If this is instead of 10K, 20K. If this resistor is 20K, then what is the VI required? What is the VI required to make this D2 forward bias? What is the input voltage required to make the D2 forward bias? This type of questions will come in the exam. How much is the input voltage required to make the D2 forward bias? This diode, I want it to be forward bias. So how much is the input required? Hemant already gave the answer. Very good. Others, please confirm what Hemant is giving. Raviteja is giving 15 volts. Hemant is giving 33.3 volts. Now you guys confirm who is correct. Kirtana is giving 15. Krishnaveni is also giving 15. Navneet is also giving 15. Find it. Very simple. See, you want this diode to be forward bias, right? This diode, you want it to be forward bias. You want this diode to be forward bias. If I want this diode to be forward bias, anode voltage of the diode should be greater than 10 volts. What is anode voltage? Which is nothing but Vx. In this case, Vx. So what is Vx? Input voltage Vi into same branch resistance is 20K divided by total resistance is 20 plus 10, 30K. So it should be Vi 2 Vi by 3. Shall I write it here? 2 Vi by 3. 2/3 of Vi is required. So how much is this required for you? 10 volts, na? Vx is required 10 volts for you. Or more than 10 volts you require. So how much is Vi required in that case? So 30 should be greater than 30 by 2. So which is greater than 15 volts. So if input is more than 15, Navneet, 2/3 of Vi greater than 10 volts is required, exactly. 2/3 of Vi is required greater than 10 volts. That gives you 15 volts. Hemant, got it? Perfect, guys. You got the concept now. Let me move on to the next question. Now it is similar to this question. It is value of Vi required to make D2 forward bias. This is the D2. If you want this diode forward bias, what is this input voltage to be? Exactly same question it is. Now just like that, see and give me the answer. Yes, see and give me the answer, guys. Come on, make it faster. Hemant, yeah. But VI is not necessarily fixed at 50 volts, right? But it can be any voltage from 0 to 50 and then 0 and then minus 50 also. Very clear. VI is required. See again 5K and 5K resistors are there. So the voltage here is always VI by 2 when this diode is under forward bias. So if I want this diode to be forward bias, this voltage should be greater than 3 volts because cathode is at 3 volts. So VI should be greater than 6 volts. So answer should be C. That's nice. Now you tell me the guys answer. You can tell me the waveform at the output for the circuit shown below. Assume ideal diode. What is the output voltage for this circuit? This is a sinusoidal signal applied 10 volts peak and to this circuit. So what is output? Come on guys, all of you please tell me. A, B, C, D are the options. What is the answer here? Now you can easily say the answer after discussing these circuits. Easily. Come on guys, what is the answer? A, B, C, D. All of you please give the answers. Raghuram is saying C. Raviteja is saying C. Very good. Ravi Shankar is also saying C. Come on, what about others? Kirtana. Piyush Kumar is saying C. Very good. Ashok is saying C. Payash, yes, very good. Payash, we are also saying C. Very good. Kirtana is saying A. Okay. Kirtana is only giving the different answer. Rest all are saying C. Hemant is also saying C. Come on guys, all of you. Come on. Nirmal Kumar is saying B. Different answer. Gaurav is saying A. Answer for this question is this. Guys, there is a twist in this. Of course, not beyond the discussion what we had. You guys are little, tricked here. The answer is A here. Sorry, answer is B here. Answer is B. Not A, not C, not D. Nirmal. Yes, Nirmal I think gave A. No. Gaurav has given A. A is, sorry, who has given B? Screen is gone for me. Gaurav has given A. Okay. Guys, the answer is B here. Answer is B here. Tell me how it is. Acha, Nirmal, you gave B. Okay, that's good. The answer is B here. How? Come on guys, how the answer is B here? Listen very carefully. It is based on the same concept what we discussed. It is same concept what we discussed. See, here 1K resistor, here 1K resistor. If you want this diode to be forward bias, the voltage here is VI by 2 because of voltage division. And it should be greater than 5 volts, right? Because cathode is at 5 volts. So how much is VI required? VI should be greater than 10 volts. For what? For making the diode forward bias. If you want this diode to be forward bias, VI should be more than 10 volts. If this diode is forward bias, then his output is 5 volts. Then. If the diode is forward bias, then only it is 5 volts. But to make the diode forward bias, how much is VI required? More than 10 volts. What is input given, guys? Peak value is 10 volts only. It is not possible to get more than 10 volts from the input applied. Yes, Nirmal, exactly. Input peak value is 10 volts. Even 10 volts is available here. The voltage here is 5 volts only. But we want more than 5. 5 is not sufficient. More than 5, not coming. That means this diode will never become forward bias, because input is not there above 10 volts. When this diode is not forward bias, it is always reverse bias. If it is reverse bias, it is just like a voltage division circuit. So output is always Vi by 2. Whatever the input is, output is half of the input. Input is a sinusoidal signal with peak value 10 volts. So output is half of that. It is 5 sin omega t. This is what? 5 sin omega t. Got it? Isn't it beautiful? Isn't it beautiful? Mark it. Mark it and write it in your short notes so that you can revise such things before the examination. In examination also this type of questions will come. Then you all guys put this answer or this answer and saying that yes, I have given correct answer. But after result, you will come to know that your question is wrong. Okay? So you have to be very careful. Understood? Any questions? Very, very important question. Mark it and revise it. Yes, guys. Next topic let's move on to is clampers. Again, clampers, I don't want to spend much time. I'm going to make it very quickly because this is a very small topic. Like clippers, we don't have too many types of clippers. Double clipper, single clipper, series, shunt, we don't have. Only two types of clampers are there. Negative clamper and positive clamper. As the name suggests, clamping. Clamping is nothing but attaching. Clamping, attaching, right? Clamp. Clamps are what? Clamps are generally for to attach, joint. So the clamper is a circuit which is to attach the waveform to a certain level. Attach the waveform to a certain level. So clipper is to clip something. Yeah. Clamper is to shift the waveform and to attach the peak levels to some reference. Manoj Kumar is saying shifting DC levels. Exactly, we can say. Yes. Okay. So clamper always will have, remember, clamper always will have a capacitor connected with a diode. And unlike clippers, you have resistor here, diode here, or resistor here, diode here. That's all different types of clippers. But in clampers, always capacitor will be here, always diode will be here. Okay. If the diode is like this, pointing down like this, it is a negative clamper. That means the clamping happens towards negative of the signal. If the diode is pointing up, then it is called a positive clamper. So first understand what is negative clamper, then obviously positive clamper can be understood easily. So let me explain this very quickly and I'll give you a shortcut also as usual. First let me explain how this is. The voltage here I call it as anode voltage. Initially capacitor is not charged, zero voltage across the capacitor is zero. And I call the capacitor voltage as Vc and the voltage here what we applied is Vi. Okay. When capacitor is not having any voltage stored across it, there is no voltage across the capacitor. When there is no voltage drop across the capacitor, then anode voltage, which is also nothing but output voltage, isn't it? Output voltage, which is nothing but anode voltage, is nothing but Vi, because capacitor voltage is nothing. Now, whenever input goes little higher than 0, if it is slightly higher than 0, capacitor voltage is 0. So anode voltage is also slightly higher than 0, anode voltage. That makes this diode forward bias. Diode becomes short. The moment diode is short, output voltage is 0. Isn't it? Output voltage is 0 because it is forward bias and it is like a short circuit. Short circuit voltage is 0. So output voltage is 0 whenever input voltage is greater than 0. Whenever input is greater than 0, output voltage is 0. Then what happens? Then since diode is forward bias and input is something higher, so there is a current flowing in this direction. Let me call this current as I. There is a loop for the current to flow. Then the capacitor is charging like this. So the voltage across the capacitor is increasing. It was 0, it is now started increasing. Voltage across the capacitor is started increasing. Isn't it? Capacitor voltage keep on increases. Now let me show you with waveform. Here I'll draw. Forget about this diagram. Okay, forget about this diagram. This is input. Whenever input is greater than 0, capacitor is charging like this, charging like this, charging like this. Capacitor is charging. Let's talk about till half cycle. When input reaches to peak value, this is Vm. When capacitor is charging like this, what is the time constant, guys? Tau C is 0, right? R into C. Since the resistance offered by the diode is 0, ideal condition, RC is 0, that means the time taken by the capacitor to charge when input is applied is 0. It is instantaneously charging. When it is instantaneously charging, capacitor voltage instantaneously increases as equal to the input voltage. That's what I have shown here. Capacitor voltage is yellow color. Reach to, let's say, peak value Vm. So capacitor voltage reach to peak value. Capacitor voltage reach to peak value. So what is this anode voltage then? The anode voltage I can also write VA is nothing but input voltage minus capacitor voltage. Isn't it? This minus this is nothing but this. Now input is at Vm. Capacitor voltage is also equal to Vm because it's charged according to the input. So output is, anode voltage is 0, which is nothing but output voltage 0. That's what we said already. But the actual thing happens from here. Up to this there is no confusion. But after this, what is after this? After pi by 2 radians, this is pi by 2, after half cycle, input is becoming less than Vm. Input is becoming less than Vm. Or otherwise, let me draw this with another color. Input is becoming less than Vm, isn't it? After this, it is less than Vm. So what happens to anode voltage? Anode voltage is according to this only. So now anode voltage is nothing but Vi minus Vc. Vi is less than Vm. It is less than Vm. Minus Vc is equal to Vm. Capacitor is already charged to Vm. So what happened? This is lower than this. That means something negative voltage it is. So the anode of the diode is something negative. Cathode is at 0 already. So what happens to this diode? Becomes reverse bias. The moment input is less than Vm, where capacitor already charged to Vm, makes the anode of the diode negative, diode becomes reverse bias. That's how it is. The diode is reverse bias. This is after pi by 2. After pi by 2 radians. After input is less than Vm again. So initially what happened? Diode forward bias, and after pi by 2 radians, the diode is reverse bias. Once the diode is reverse bias, it is like this. Now output voltage is simply, what is capacitor voltage now? It is equal to Vm. Capacitor already charged to Vm, and once the diode is reverse bias, it cannot discharge because there is no path for the capacitor. It cannot discharge, it remains at Vm only. There is no path for the resistor. There is no path for the capacitor to discharge. It's open. So it remains at Vm only. So what is output voltage? As we just discussed, Vi minus Vc. So what is Vi? Vi is less than Vm, whatever it can be. It can be this, it can be this, any value it can be. It is Vi value, corresponding Vi value minus Vc. Vc is already sitting at Vm. So it is going to be something negative. let's say for example Vi is equal to 0, some certain points, because we know these points, we don't know how much is this, we don't know how much is it. If you substitute certain points like this, these certain points if you substitute, we can find output voltage for different values of the input. When Vi is, let's say Vi is 0, then what is V0? V0 is 0 minus Vm is minus Vm. When Vi is minus Vm, it can reach to minus Vm value also. If it reaching to minus Vm, then V0 is equal to minus Vm minus Vm. So it is minus 2 Vm. Similarly, when Vi reaches to again 0, after Vm it reaches to 0, then again V0 is minus Vm. And if Vi reaches to Vm, then output voltage is Vm minus Vm is 0. Even input comes to again Vm, diode will not become forward bias, because if you want this diode forward bias, the voltage here should be positive. Never happens. If you want this voltage to be positive, Vi should be greater than Vm. Never is happening. It's never going to happen, because input highest is available as Vm only. If you want this diode again to forward bias, Vi has to be greater than Vm, not going to come now. So it will never be. So that's why the output voltage always follows this equation, As per the input, output will be correspondingly like this. If you join all these points, at pi by 2 its value is 0, till this it is 0, till this it is 0, isn't it? It is 0 like this, up to that. And after that what happened? When it is 0, it is minus Vm. When it is minus Vm, it is minus 2 Vm. It is 0, it is Vm. And again it is 0, Vm it is 0. And 0 it is minus Vm. And I am just joining all the corresponding points. Sorry, this is 0 means minus Vm, and Vm is 0, and again this, and again like that. So if I join all these points, I am going to get a sinusoidal waveform like this. See what happened? The waveform has been shifted down. The shape remains same. Yes, Rupesh, I do that. Okay, the shape remained same. See, it is after pi by 2 radians. The shape is same as sinusoidal only. Only thing is the waveform has been shifted down. You can see the waveform has been shifted down and clamped to zeros. These positive peaks of the input waveform are clamped to zeros. That's why it is also called as positive peak clamper. Positive peak clamper. Or it is also called as negative clamper. It's called as negative clamper. Why it is called as negative clamper? Because the waveform is shifted to negative half cycle, negative side. The average value of this is something negative now. The average value here is 0. That's why it is called DC inserter also. Okay, Ravi Shankar, I do. Clear? But if you are not into this all discussion, I can give you a shortcut, trick and shortcut again. Okay, so let me give you the shortcut to you. This all explanation is over. If you want all this explanation, you can go. Otherwise, I'll give you a simple technique and shortcut to this to understand how this is. See here. The diode is pointing down. See, to first decide whether it is clamper or not, you have to have a capacitor, you have to have a diode. Diode capacitor combination. Capacitor here only, diode here only. That is a clamper. That's it. So the capacitor charges only once during the whole shifting, sir? Yes. Yes, Raviteja. That too, first quarter cycle only. First pi by 2 radians only, it charges. After that, the capacitor voltage remains, if you want to show the graph, I'll show the capacitor graph also here. You can see yellow color represents the capacitor voltage. Capacitor started charging. After this, its value remains at Vm only like this. This is Vc. Capacitor voltage retains at Vm always. Yes, Payash, I do that. Yellow, white, green. Got it? Now that shortcut technique. Shortcut and technique. If the diode is pointing down like this, it is a negative clamper. It is clamping, it is showing downwards direction. That means below 0. So remember that it is a negative clamper. Okay? But where the clamping is happening, see where the cathode is connected to. Cathode is connected to ground, that means 0 volts. So clamping happens to 0 level. That's what here waveform. That's what here you see. Clamping happens at 0 level. This is 0 level. Na? This is the clamping happening. Suppose if there is a battery of 2 volts here. Clamping happens at 2 volts. Shifting down, but clamping happens at 2 volts. How the waveform is expected to have? Let's say this is 2 volts level. How the waveform is expected now? Just a second. How the waveform? First quarter cycle it is 0. After that it is like this. This is a clamping. Why? Because it is connected to 2 volts. Okay. Done? Like this. Suppose if it is connected to minus 2 volts, like this, minus 2 volts. Then clamping happens to minus 2 volts. Shifting down is happening. Right. Next is this circuit. So now without doing anything you can say. So this is pointing up. That means clamping happens shifting up. Where? Because this is connected to 0. So clamping must happen. Clamping must happen like this. Something like this. I'm not following exact scale here. Pardon me for that. Yeah, positive clamper. Clamping is happening upwards based on the direction. Clear? Very simple like this. Hope it is clear for you. So there are only two basic clampers, negative clamping and positive clamping. And where the clamping happens depends on whether biased or not. If it is connected directly to the ground, clamping happens to 0 level, otherwise some other level. Okay? Yeah, now move on to the some questions here. It is very simple. Find the correct option for VO. The circuit is this and input is this. So clearly it is shown that it is shifting down and clamp to 0 level. Okay, so clamp to 0 level should be this cannot be the answer. This cannot be the answer because they are shifting up. So this one or this one. This one is the correct answer, as peak to peak value is 2 volts here. So here also, here peak to peak is. So once clamping happens, waveform is not changing. Shape, peak to peak will not change. So B should be the correct answer. And this one, guys, determine what is V naught. Determine V naught. This is showing upwards. So clamping has to happen up. So if any downward clamping is there, that cannot be the answer. But clamping cannot be at 0 level. Clamping has to happen at 5 volts. So this cannot be the answer. This cannot be the answer. Either this or this can be the answer. So which one is correct answer in that case? So you have to see peak to peak voltage. Here peak to peak is 30 minus 5, 25. But here actually it is 10 minus of minus 10 is 30 volts. Peak to peak is 30 volts. So clamp to 5 volts, peak to peak is 30. This is the correct answer. A. Very good. So this way you can work on. So this one also you can say, guys. Come on, this one you can take it as homework then, because we are running short of time. Let's make it faster. Already 1.5 hours it is. This you can work on then, okay? Then voltage doubler. Voltage doubler is similar to, not exactly same, it is similar to clampers, clamper and a peak detector. Combination becomes voltage doubler. Just checking swing of the waveform, sir. Yes, exactly. Okay. Direction of the diode is important. Which direction? So what is this, guys? To explain you what is doubler, so I'll show you doubler as a breaker. It's not a doubler. Actually, it is not a doubler. I am constructing the doubler. Okay. What is this? This is a capacitor and this is a diode. So what is this? Positive clamper or negative clamper? Come on, positive clamper or negative clamper? So it is shifted up. So here what we do is, the waveform here is what? Let's say this is the waveform connected. If this is the waveform connected, and if I say this is 0, this is 0 volts. Okay. How the waveform is? The waveform here is like this. And here it is, let's say it is Vm. This is 2 Vm. Correct, na? This is how the waveform is. This is 0. This is what the clamper, right? Clamping up to the 0 levels. Positive clamper. Now what I'll do is, I'll connect this to a diode here and then a capacitor here. This is output, I call it as. This is another capacitor, C2. This is a doubler now. This is a voltage doubler. Why? Now for this yellow part circuit, what you applied? This waveform is applied. So this diode will become forward bias for the positive half cycle. During positive half cycle, this diode is forward bias. So this capacitor will charge to what? 2 Vm, right? This capacitor will charge to 2 Vm. So the voltage here is 2 Vm and it retains at 2 Vm. So this is the waveform. So how the capacitor voltage is? I'll show you the capacitor voltage also here. Let me draw with green. Okay. How the capacitor voltage is? So when this diode is forward bias, capacitor is charging like this, plus minus. How? From 0, it is charging up to Vm. After that, it retains at Vm. This is 2 Vm. Because input for this capacitor is 2 Vm. So up to 2 Vm, it charges like this as per the input. After that, it remains at 2 Vm. That's why it is called doubler, voltage doubler. So that is the circuit we can see here. We can call it as C1, C2, D1, D2. So V0 is 2 Vm is the doubler. I can give you a pattern here. Okay, every time you need not to remember voltage doubler. You can work on a pattern here. See here, I'll redraw this circuit here. See, this is like this. It is just to, this is actually doubler, right? If you want tripler, quadrupler, how? Every time remembering every circuit is difficult. So let me give you a shortcut for that. So this is the capacitor, this is the diode. This is what input is, okay? This terminal is nothing but this terminal. Now what I'll do is, I'll connect diode like this, and this capacitor is between cathode and anode of the diode. So this like this, okay? Now what I'll do is, I'll connect one more diode like this, and put one more capacitor like this, and one more diode like this, one more capacitor like this. So one more capacitor like this, one more diode like this. It is up to you now where to go. etc., etc. Now what is happening? This capacitor is charging to Vm, this capacitor is charging to 2 Vm. So what this capacitor will charge to? It is to Vm, and this is to Vm, this is Vm, to Vm, etc., etc. Now if I take the output here, that's what this circuit is. So what are you getting here? 2 Vm. Suppose if I take the output here, what I am getting? Vm. If I take the output here with respect to this, so I'll get 2 Vm and 2 Vm, it is 4 Vm. If I take the output here, and this is 2 Vm, no? This is 2 Vm. Sorry, 2 Vm. So this is 2 Vm and Vm, it is 3 Vm. So if I take the output here, it is 5 Vm. So if I take the output here, it is 6 Vm. So if you take the output, if you take only this circuit, this is doubler, this is tripler, quadrupler, 5 times, 6 times, extend it any times. And you observe a pattern here, diodes are following this pattern, right? This pattern like this. So you can keep on extending that. I just plot this, I have not done anything new here. This only I have drawn in a different way and extended. So that gives you any clamper you want, sorry, any doubler you want. Doubler, tripler, quadrupler, etc., etc. Isn't it? Remember, this is very important. Done. Rectifiers, guys, I am going to finish it very quickly because the rectifiers is very small and easy topics. If you have any questions, keep asking me. So far, everything going fine? Come on, guys. Everything going fine? Or you have any questions, suggestions? Come on, you have any questions, suggestions? Keep asking me. Sir, where it is used? Wherever you want this input voltage to be doubled. But Raviteja, it's a very good question. You know, that is very important that the capacity of the diode and capacitor should be sufficient enough. Here, for example, in this question, let's say input is 20 sin omega t. Okay. And if I take the output here, it is 6 times. That means 120 volts you are getting here, right? 6 times the input peak. That means 120 volts. That means the diode what you connect here and the capacitor what you connect here should be capable of handling that much voltage. Okay. Nothing is coming anything extra, because these capacitors are, each capacitor is having 2 Vm, 2 Vm, 2 Vm. You are taking output from here to ground, that's why all these 3 are added up. But the diode should be capable of handling 120 volts, otherwise diode gets damaged. Capacitor also should have the rating up to that, otherwise this circuit is not valid. Right. Everything going good now? Now let's go ahead. Rectifiers. As you all know, rectifiers is a circuit to convert AC to DC. In broad we say like that, but exactly every rectifier cannot convert AC to DC directly. It converts an alternative signal to it can convert an alternative signal to an unidirectional signal. A bidirectional signal is converted to unidirectional using a rectifier, where that unidirectional signal will have some DC. That's what rectifier is. A circuit converts oscillating 2-directional signal into unidirectional signal. We will extract DC from the unidirectional signal. That's what rectifier circuit is. So there is a pulsating DC otherwise. There is a misconcept that students may be thinking that rectifier circuit will give DC directly. No. It just converts bidirectional signal into unidirectional signal. Rest we have to do that using filters, smoothness, etc., etc. There are different types of rectifiers, you know already. Half wave rectifier, full wave rectifier, bridge rectifier. In fact, these two come under full wave only, because full wave rectification happens. That means full wave is converted into unidirectional, whereas in half wave only half wave is converted into unidirectional. After the filter, I will get a pure DC. Exactly, Pankaj. So let's see the complete. As I just told you, rectifier is just converting AC to DC is not correct. It is converting AC to unidirectional signal. Then if you want to get the pure DC, perfect DC, then there are some more circuits are required, like this. So generally we go for this household supply to convert. Then first we use is step down transformer to step down to the required value of the DC, because the DC is to be as per our requirement, maybe 5 volts, 7 volts, 10 volts, 15 volts. How much is the final DC you want? As per that, the signal household supply has to be stepped down to. If I want 10 volts, I have to step down to accordingly. If I want 3 volts, then I have to step down accordingly. If I want 50 volts, then I have to step down accordingly. That is why step down transformer is very important and required. Then this rectifier. So here the sinusoidal signal household supply is sinusoidal. Step down transformer output is also sinusoidal. Only difference is the magnitude. Rectifier output is maybe like this, based on what type of rectifier you are using. Then you have some DC. This is the DC something is available. So that is possible to get like this using a circuit called, again, a filter. That filter can be L filter, C filter, LC filter, etc. And then a regulator. After the regulator is a regulated DC. We call it as regulated DC. There is a difference between just DC and regulated DC. So that DC is constant. It will not vary with respect to variations at the input or load. That's what regulated DC. We'll be going to see what is regulator and how the regulator is. We'll be going to see rectifiers. We'll be going to see filters. But in very brief, step down transformer need not to explain. You already know, right? So this is the complete process to convert AC to DC. It's not just by rectifier. So these many circuits are there to get that. Anyhow, one by one, our interest is half wave rectifier. Now it is very simple for you. Half wave rectifier is going to be, why? After studying clippers, clampers, rectifier is very simple. So this is the step down transformer as we know. So 230 volts is stepped down to the voltage we wanted. Let's say that is Vm sin omega t. How much is that Vm sin omega t? Depends on this turns ratio N1 and N2. Based on the turns ratio, we can get this Vm value anything we wanted. If I want 230 volts, this is RMS value in fact, 230 volts RMS to be reduced to 20 volts, we can do that by suitably selecting the turns ratio. And then the diode becomes forward bias or reverse bias based on what the voltage here is, positive or negative. And you all know simply that it is forward bias, the voltage is same as input. For negative half cycle, the output is going to be 0. That means output is going to be only positive half cycle like this. This is how the rectifier output is. Is it clear? Sir, what is the function of regulator? I'll show you, Ashok. Just wait for another 10-15 minutes. We'll be dealing regulator as well. Regulator plays a very important role. Even though regulator input is DC, output is DC, but still we want. Okay. So this is going to be the output, or we can say this half wave rectifier is simply behaving like a negative clipper. The negative half cycle is not coming now. This is clipped off because diode becomes reverse bias during that time. So that part is open. So remaining waveform is available. So input to the waveform is, input to the circuit is full cycles, positive or negative, having AC equal to AC signal what we applied, and the DC in the input waveform is 0, whereas output is having only positive half cycles. So there is some average value. Average value is nothing but DC value. Average value or DC value same. That is what it is doing. So how much is that? We can see. See, this is what? Half-wave rectifier. When the diode is under forward bias, it is short circuit like this. So only positive half cycle comes like this. During negative half cycles, the diode is reverse bias like this. So output will be 0 like this. It is 0 during negative half cycle. So that's why you are getting only positive half cycle. That's why it is called half wave rectifier. Only half of the wave, positive half cycles are only available at the output. But there is a problem here. What is the problem with half wave rectifier? Come on guys, anybody can explain what are the problems with half wave rectifier? There are many problems. There are many problems with half wave rectifier. Why? Efficiency is less, ripple factor is more, transformer utilization factor is not sufficient, DC is less, AC is more, such all things are there. So half wave rectifier is practically not preferred because efficiency is very less. How much is the efficiency? Efficiency is 40.6. That means only 40% of the signal applied at the input is converted as DC signal. Very, very less, na efficiency. We expect the efficiency close to 100% always. All those values I will give you in a tabular form, don't worry, I will summarize all these things. That is the reason why we go for full wave rectifier. Why full wave rectifier is required? We want the efficiency to be close to 100%. So in full wave rectifier, we will get this efficiency 81.2, double the half wave rectifier you will get. 81.2 is the efficiency you will get full wave rectifier. Yeah, Hemant, half wave rectifier ripple factor is also very high, 1.21. So ripple factor should be always lesser and lesser. That tells you how much is the ripple, AC component available at the output. Since it is a AC to DC converter, ripple should be as low as possible. So here in full wave rectifier, ripple factor is also reduced to 0.48. Whereas in half wave rectifier it is 1.21. That's why full wave rectifier is better. But remember, full wave rectifier uses a center tapped step down transformer. This is a center tapped step down transformer. And it uses two diodes, D1 and D2. D1 conducts positive half cycle, D2 conducts negative half cycle of the input. That means both the half cycles are converted into positive half cycle, where D1 becomes forward bias for positive half cycle, D2 becomes forward bias for the negative half cycle, so that output will be forward bias, again forward bias by the second diode like this. So all cycles, positive half cycle and negative half cycle. This is this one VS2 and this is VS1, secondary voltage, because it is a center tap voltage, center tap transformer, step down center tap transformer. This is, and this voltage VS1 and VS2 are exactly 180 degrees out of phase because of the center tapping it is. So this is because of D1, this is because of D2, this is because of D1, this is because of D2. This is D1. So this is the output you will get for a full wave rectifier. Okay, that is why efficiency is very large you will get, ripple factor will be less, because the average value here is VDC we call it as, which is 2 Vm by pi you will get. Whereas in half wave rectifier, this is half wave rectifier na, VDC is equal to Vm by pi you will get. So in full wave rectifier, DC value is double the half wave rectifier. So it is 2 Vm by pi it is. Yeah, half wave rectifier it is Vm by pi, full wave rectifier is 2 Vm by, double the half wave rectifier DC. That's why full wave rectifier is better than half wave rectifier. But still there is a problem. Problem is center tap transformer. Center tap transformer is generally bulky, costly, and noise also will be more. That's why we don't prefer center tap transformer, but we prefer this type of waveform. We want this type of waveform, but that too without center tap transformer we want. That is why we go for bridge rectifier. As I just shown, this is reverse bias for negative half cycle, positive half cycle, and this will be reverse bias for negative half cycle, and this will forward bias for negative half. So that is why output we got. And the bridge rectifier is with only step down transformer, not with the step down transformer, center tap. center tap step down transformer is the problem with the full wave rectifier. That's why we go for the bridge rectifier, where it is called bridge rectifier because these diodes are connected in the shape of bridge, nothing more than that. So we are using 4 diodes here, D1, D2, D3, D4. During positive half cycle, input is sinusoidal, right, like this, and it is stepped down, it is also sinusoidal again. Only difference is magnitude. So during positive half cycle, it is like this. During positive half cycle, these 2 diodes, D1 and D3 will reverse bias, and these 2 diodes will become forward bias. If that is the case, the current will flow like this, like this, like this, like this, and through the diode, through the resistor like this. This current direction is very important, guys, here. See, like this to the another diode and like this. So this is the starting point of the current and this is the ending point. So current is flowing in this loop like this. So when current is flowing like this, see the direction of the current. Voltage is dropped across this, that is what VO we call it as. Positive or negative it is? Positive. Navneet, I will explain. So this is positive half cycle, you are getting the output also as positive like this. During negative half cycle, this is how the negative half cycle is. During negative half cycle, this diode and this diode are reverse bias, and these 2 diodes D1 and D3 are forward bias. So how the current is? During negative half cycle, this is positive, this is negative. So the current will flow like this, like this, like this, and see like this, and to the negative like this. See, starting is this, ending is this. But see the direction of the current. How the direction of the current? In the same direction as earlier. So again you are getting a positive half cycle. So during negative half cycle also you are getting a positive half cycle like this. Earlier also you got a positive half cycle like this. Next again you will get a positive, next again you will get a positive, next again you will get a. So for every negative half cycle, these 2 diodes forward bias. For every positive half cycle, these 2 diodes will forward bias, so that you will get a complete cycle like this. So which is exactly like full wave rectifier. Then why we go for this? To avoid the center tap transformer, because here we use only step down transformer. So this is the best rectifier we got in terms of efficiency, in terms of PIV, etc., etc. I'll explain what is PIV. Hope this explanation is more than sufficient for you, because explanation se zyada ye important hai, concept and formulas here in rectifiers, and how the behavior of the diodes, etc. This is a summary, as I told you, summary of all the rectifiers. VDC for half wave rectifier is Vm by pi. For full wave rectifier, 2 Vm by pi, double the half wave rectifier. Bridge rectifier also same, because these two are full wave rectifiers only. Output of this and this is exactly same, only difference is the circuit. Okay. PIV is peak inverse voltage, I think, but Navneet is asking about not the full form. He may be asking about what it is and how it is to be found. I'll tell you. RMS voltage, because output is having some AC, so how much is that? It is Vm by 2 here, Vm by root 2 here, Vm by root 2 here. Efficiency, which is very important for us. Very, very less in half wave rectifier, full wave rectifier and bridge rectifier, it is best. Ripple factor, it is denoted with gamma. Efficiency denoted with eta. 1.21, it is very large. Here it is better and here it is also better. Form factor, it is simply the ratio of VRMS to the VDC. It is 1.58, 1.11 and 1.11. Obviously, form factor should be as low as possible, because VRMS by VDC, VRMS should be as low as possible. Peak factor is another parameter, which is the ratio of Vm by VRMS. It is 2 here, root 2 here, root 2 here. And TUF, it is called transformer utilization factor, another important parameter. How much of the secondary of the transformer has been utilized to convert AC to DC? It should be as high as possible. It is 28.6% here, 68.9% here, 81.2% here. That is why bridge rectifier is better than full wave rectifier, the second reason. Then PIV rating. PIV rating, in fact, I'll write it as PIV rating required. PIV rating required for half wave rectifier is Vm, full wave rectifier is 2 Vm, bridge rectifier is Vm. First, here I'll explain two things. Okay, I'll explain two things. One is what is PIV. Second is how much is for half wave rectifier and how much is for full wave rectifier or bridge rectifier. So first let us understand what is PIV. Peak inverse voltage is the voltage what we can apply maximum to a diode when it is under reverse bias. It is nothing but the rating of the diode. Suppose when you buy a diode, its PIV value is given as 30 volts. That means you should not apply more than 30 volts when it is under reverse bias. What happens if you apply? Simple, you need to buy another diode because its capacity is to handle up to 30 volts only. More than 30 volts, it gets damaged. That is the meaning of PIV, peak inverse voltage. Maximum reverse voltage that can be applied to a diode under reverse bias. Okay. VDC average value same. Kitna? Yes. VDC or V average is same. Okay. Now, PIV rating required for half wave rectifier. PIV is for what? Diode it is. When you are having a diode connected in half wave rectifier, what should be the rating of the diode? In bridge rectifier, what should be? In full wave rectifier, what should be? In half wave rectifier, it should be equal to Vm. In full wave rectifier, it should be 2 Vm. Bridge rectifier also, it should be Vm. How it is found? It is different for different circuits based on the circuit it is. So how to find? It is very simple. All of you see here. How much is the rating of the diode required for a circuit to find? Half or full or whatever. Is just find the voltage across the diode when it is under reverse bias. For example, this is the diode under reverse bias, right? You find how much is the voltage across this, that is the PIV rating required. So this point is nothing but this point. This point is nothing but this point. So voltage across this diode is nothing but voltage across these two terminals. How much is maximum possible? Vm only. That's why PIV rating required for this full wave rectifier or bridge rectifier. This is also called as full wave rectifier, of course. The PIV rating required for this diode to connect here in the bridge rectifier is Vm. Same way for half wave rectifier also this. Same way it is for half wave rectifier and full wave rectifier. In full wave rectifier, if you see this is how the full wave rectifier is, right? See, for example, this is the diode reverse bias for some case. How much is the voltage across this? This terminal is nothing but this. This terminal is nothing but this. So voltage between these two terminals is nothing but PIV rating of the diode required. Rating required means what rating of the diode, what capacity diode you need to connect there. Here the voltage across these two terminals of this diode possible 2 Vm it is, isn't it? From here to here, here is 1 Vm, another here is another Vm, 2 Vm it is. 2 Vm voltage. Suppose if you are having Vm sin omega t, Vm sin omega t is the secondary voltage. If Vm is 50 volts, you cannot have a diode with 50 volts PIV rating. You have to have a diode whose PIV rating is 100 volts in this case, which is a drawback, isn't it? Higher rating diode is always costlier. That's why if you go for bridge rectifier, same 50 sin omega t is applied to the diodes where diode rating required is only 50 here, because Vm we found is 50 there. So PIV rating required for a bridge rectifier or half wave rectifier or full wave rectifier is very important parameter. It tells you what diode rating has to be connected there. Okay. Hope that is clear for you. So seeing these all things, what is better? Obviously bridge rectifier is better, isn't it? Bridge rectifier is better. So what is output frequency? Double for bridge rectifier and full wave rectifier, and it is same as input frequency for half wave rectifier. So I think this is not surprising for you. Okay, that is based on the waveform you can see. Then coming to the filters, guys. Filters, I'll wind it up very quickly. Why we need filters? As I just told you, to smooth the waveform. output of a rectifier is not perfect DC. So to have perfect DC, we need a filter. Navneet, more PIV is better, na? No. A diode having more PIV rating is better. But for a circuit, lower and lower the PIV rating of the diode required is better. It is simple like this. How you want your worker? You want a worker who charges you more or who charges you less? Right? Who charges you less is what you want. That is what PIV rating required for a circuit. What type of worker you want? Who can handle more work or less work? Whose capacity is more or capacity is less? Capacity is more. Capacity of the diode is PIV. As a cost point of view, in the circuit, what is better? Less PIV rating requirement is better. You can interpret like this. Okay, I'll just show you L filter, inductor filter, how the inductor filter is. So this is the bridge rectifier. Output of the bridge rectifier is this. Generally, we connect this to a load here, RL. This is the output we call. But we want to have a filter. So what we do is, we don't give this output directly to the load. We will connect an inductor here like this, and then a load is connected like this. This is what VO, and this is RL, and this is L. This is called inductor filter. Right? You all know that inductor XL. Inductor will have XL equal to 2 pi FL, whose value is equal to 0 for F is equal to 0, whose value equal to infinite for F is equal to infinite. Isn't it? That means inductor allows zero frequency signals and blocks higher frequency signals. The output of this bridge rectifier will have AC plus DC both. Pulsating DC, na? The voltage here is this type of waveform, which is varying with respect to time, but average value is not equal to 0. So what this inductor will do? Will stop this variations in the signal and allow the DC to pass through it. So the DC is passing through the load, so you will get the DC. That is the easiest and simplest way to explain an L filter. Okay, got it, guys? Because inductor blocks AC, allows DC. DC is passed through the inductor to the load. AC is blocked by the inductor, so that load gets only DC. And the ripple factor, you can find this formula you just by heart. I don't want to derive this here, because ripple factor decides how much is the ripple available. And you can see here, ripple factor should be required always as low as possible, as I just told you. It depends on the inductor value L. If L is more and more, then only ripple factor is smaller and smaller. That means to have better DC, ripple factor is smaller means better DC. To have a better DC, inductor value should be as large as possible, which is practically a problem. That is why we don't use L filter only. Larger value of inductor gives you more noise. Size occupied is also bigger. So that is the problem with the inductor. That's why we don't practically use this. Of course, we can use, but this is a drawback. So that's the reason we go for another filter, which is capacitor filter. This can be connected to even bridge rectifier also. So what is capacitor filter? Capacitor filter, we connect a capacitor here. We connect a capacitor here. So what is capacitor speciality? XC is equal to 1 by 2 pi FC, 1 by 2 pi F into C. So its value equal to 0 if F is equal to infinite, its value equal to infinite if F is equal to 0. It is reciprocal to the inductor. So that means it allows the AC signal to pass through it and it blocks the DC signal to pass through it. Here we have AC and DC together, output of the rectifier, half wave or full wave or whatever. So the AC is passed through the capacitor. It allows less resistance for the AC signal to pass through. So AC signal will pass through the capacitor to the ground like this, but the DC will go like this. DC will go like this, so the voltage you get is DC. That's how this is working as. Okay. I think this is not L. This is, guys, please correct this. This is RL, R suffix L. R into L. Correct this. This is the ripple factor. Formulas for half wave rectifier and full wave rectifier. So to have smaller and smaller ripple factor, capacitor value should be higher and higher. Capacitor should be higher and higher. It is okay. We can connect higher value of capacitor. Doesn't take much space to connect. So that's why higher capacitor is also okay. That's what C filter is better than L filter. If there is a question, whether capacitor filter is better or inductor filter is better, go for capacitor filter. Okay, in terms of practical application. Then LC filter is a combination of C and L. So you can connect an inductor here and then a capacitor here and then the load what you want. So this is the output. This is RL, this is C and this is L. So this blocks AC, allows the DC. If at all any further AC is there, pass it through the capacitor to the ground and blocks the DC. So entire DC will pass through the pass through the resistor, so that you'll get perfect DC here. Okay. So this is XC, guys. This is X suffix C. This is X suffix L. Okay. This is LC filter. One more level of filtering if you want, then you can go for CLC filter. CLC filter is another level of filterings. Capacitor, then inductor, then capacitor. Working remains same. So this is 2 levels, 3 levels. So here is a capacitor first, then an inductor, then a capacitor, and then a resistor like this. RL, C, C, L. CLC filter. This is also called as pi filter because this is in the shape of pi. So you can also call it as pi filter. This is CLC filter. Sai, at the revision, I don't think we can discuss those things. It's a very simple thing you must know. CLC filter it is, right? So capacitor allows the AC to pass through it. If at all anything is there, blocked by the inductor. If at all anything is there, allowed by the capacitor. So only DC goes through this. So not only like this, another name is pi filter. So you can further go for many more combinations like this: capacitor, inductor, again inductor, again capacitor. Like this, it depends how many capacitors, how many inductors you want to connect. Depends on how better you want the DC. More and more the pi filters connected, better and better the DC is always. Okay. Right, guys. So some questions, I think these are simple questions. You can go for this as a homework. IDC and IM and IRMS of half-wave rectifier. RL is 1K, VM is 30. So what is IDC for a half-wave rectifier? What is IM for a half-wave rectifier? What is IRMS for a half-wave rectifier? So I told you already, IDC is IM by pi, it is half-wave rectifier. Like VDC is VM by pi, IM is IDC by pi, IDC is IM by pi. So peak value, IM is nothing but peak value, which is nothing but VM by RL. VM by RL. So 30 by 1K, it is 30 amperes. 1K na 30 milliamperes. So 30 milliamperes by pi. 30 by pi milliamperes is the answer here. RMS is IM by root 2. Sorry, IM by 2 na, half-wave rectifier na it is. So IM by 2 it is. So it is 15 milliampere. Okay, it is for half-wave rectifier. So rest of the problems also you can do this. So this I want to give it as homework because that problem I already have given. half-wave rectifier, the value of direct current IDC is given. This is IDC, where IM is the peak. IM is the peak to peak value. Remember, peak to peak value it is. Find the value of X. Very simple question it is. You can do this. Can you? Can you guys? Hope you can. This I'll tell you. The average value of V0 is here. Come on guys. This you please try this. This is a very good question. This type of questions will come in the gate examination. This type of questions will come. Raghuram, X equal to Pi. Pi you are saying. Could be, I don't know. I have not done it. Please do it. Maybe it is. Check it. Come on, this is very important guys. What is the average value of the output? If you want average value, first you need to know what is the output value, right? This is omega t, this is VO. You need to know the VO shape first. If you know the VO, then you can find what is the average value. So try to find the output voltage. Where is the output voltage? Here. This is the output voltage. You find what is this, then average value is very simple for you. Come on guys, are you there? Are you there? And after these problems, we are going to enter into the BJT, biasing and amplifiers. Most important, come on guys, make it faster. We are running short of time, make it faster. Biasing, will finish it, and then amplifiers, then feedback amplifiers and multistage. Feedback and multistage can be done very quickly. Biasing and amplifiers is very important gate point of view, and I'm going to cover this after 5 minutes maybe. Come on. Do you need a break guys, or shall I continue? Do you need a break or shall I continue? It is up to you. Ravi Shankar is asking break. What about other students guys? You want break or shall I continue? If there is a break, only 5 to 8 minutes, not more than that, because we have to finish rest of the topics faster. I'm sure I'll be finishing that before 8:30. Because 2 more hours are there, 1 hour for biasing and amplifiers. Another 1 hour for feedback and multistage. Yeah, 5 minutes break, right? By the time I'll come back after the break, you have to give me the answer for this, okay? So break for just 5 minutes guys. Break for 5 minutes and quickly come back. Don't leave the channel. Don't leave the channel. Quickly come back. Now it is 6:23. So I'll be again coming back at 6:30. Back at 6:30 p.m. Back at 6:30 p.m. Done? Come on guys, all of you please come with the answer. Don't go anywhere, stay tuned and inform other students also. After this, I'm going to start with BJT, biasing, amplifiers and most important techniques, quizzes. I'm going to give you that. Okay? Done guys, thank you. Yes guys, welcome back to the session. Hope I am audible to you. Please confirm that I am audible. Please confirm in the chat box that I am audible, visible to you. Yes guys, come back from the break. So let me strike it off. Now break is gone. All clear? Very good. So let me start again then. Come on guys, please inform everyone else also that we are resuming the class to finish the syllabus on time, and rest of the students also. All clear? Great. Thanks guys for staying with us, and also help us hitting the like button, share to other students. You know, not only you guys, rest all also should get benefited. That's what our intention is. Please share it to other students. Very good. Back with a lot of energy again, right? Right. The answer is some students are saying 5 volts, some students are saying 3.1. Nirmal is saying 3.18. Yeah. I think Nirmal is correct. Answer A is correct for this. A is correct. I think so. So let me explain this. This is 10 sin omega t, right? During positive half cycle, so this diode will become forward bias. This diode is reverse bias. That's what during positive half cycle happens, isn't it? If this is the diode, how the current is? Current is like this. I am showing with yellow color. This is how the current direction is. It divides here. This is a junction. Current divides here like this, and this is open anyhow. So current is coming like this. This is coming like this, and they are meeting here. So here current is getting divided between 2K and 2K. So when current is divided, the voltage drop here and here is also proportional. Since these two resistors are equal, the drop across this and this across this is also same, equal, because the resistor values are equal. So out of 10 volts peak, it is sinusoidal only. 10 volts peak value, 5 volts is dropped here, 5 volts is dropped here. But our interest is this. This is output voltage. So it is a sinusoidal signal with peak value of 5 volts. Or if I want to draw, let me draw with input waveform as well. Let's say this is input waveform, so that you will understand clearly. Okay, now output is this one, 5 volts, because it is like an attenuator. Once this diode is forward biased, it is like an attenuator, right? 5 volts. Input peak is 10 volts. This is 10 volts, but output peak is 5 volts, because it is divided across 2 and 2. Now, during negative half cycle, let me change the color. Change the color of the pen. Let me take green this time. During negative half cycle, this is negative with respect to this. So what happens? This diode will become forward bias. This diode will become forward bias, isn't it? So how the current flows? See this green color this time. So current flows like this, and also like this. Current also will go like this, because this is a junction again. Current is dividing here and here, this way and this way. And this current flowing here will go like this, because this side is open. This diode is open now. So this current is going like this and meeting here and passing through the ground, passing through the diode and reaching the negative. Just a second. Reaching the negative, right? Though resistors are in parallel, sir, how voltage? When resistors are parallel, then only division happens, na? When resistors are in series, division will not happen. But my interest is how much is the voltage across this. This green color current is flowing like this and like this. So there is a voltage drop across this. This is what my output voltage. Again, it is in the same direction as the positive half cycle. What we are talking about? Negative half cycle. So this is a negative half cycle I am talking about, but the voltage what I got here is positive. Because output is taken across this and the current is also flowing like this. So again, it is divided across 2K and 2K. So same 5 volts is available. So again, positive 5 volts is available like this. I am talking about negative half cycle, but the current, see how it is flowing. So the voltage drop across this is positive only. So again, I am getting a positive half cycle. So it repeats. Again, negative half cycle, positive half cycle again, it will be positive half cycle of 5 volts peak. And again, negative means it will be positive half cycle of 5 volts. So this is the output waveform. Now we need to find what is the average value of this output waveform. VDC or V average is equal to how the waveform is, like full wave rectifier it is, or bridge rectifier output. So how much is that? 2 Vm by pi, because it is exactly like full wave. So it is a full wave rectifier or it is a bridge rectifier. It is like, not exactly in fact, it is like a full wave rectifier or bridge rectifier. Why I am calling it a like? Because you are getting the same waveform. It is like. Then why we need full wave rectifier and bridge rectifier we discuss? What is the difference? This is definitely not a better circuit than full wave rectifier and bridge rectifier what we discuss. Why? Because here full half cycle is not there. Suppose if it is a bridge rectifier or if it is a full wave rectifier, we would have got this type of waveform. This type of waveform we would have got. Then what is the DC we would have got? Again 2 Vm by pi, which is 2 into 10 by pi. But here what we got? Here what we got? Here it is 2 into peak value is how much? 5. 5 by pi. That is 10 by pi it is. I think 3.18 is correct. Suppose if the same signal is given to the full wave rectifier or bridge rectifier, we would have got double of this, 6.36 we would have got. So that's why this circuit is not better compared to the full wave or bridge rectifier. So the answer for this question is A, 3.18. Clear now? Clear no? Any questions you can ask? Now you tell me this, what is this? DC voltage of V0. Assume diodes are ideal. What is the DC voltage? DC voltage is nothing but average voltage again. Again, if you want to have the average voltage, you have to have the output voltage first. Draw the output voltage first. VO. Plot the VO. So what is given? 5 sin omega t. So if it is positive with respect to this, what happens? This diode is reverse bias. This diode is also reverse bias. So then output is 0. First half cycle it is 0. Then negative half cycle. Negative half cycle, this is negative, this is positive. So what happens? So this is positive. So this diode is forward bias. So this diode is forward bias. Okay. And the same positive is applied to this. So this diode is also forward bias. So both the diodes are forward bias. Now it is connected like this. So how the current direction is like this. So positive, negative, output we are taking like this. So positive half cycle you are getting. So 5 volts positive half cycle you are getting. This is 5 volts. 5 volts positive. Again positive half cycle it is 0. Negative half cycle 5 volts. Like this. So what you are getting? It is like half-wave rectifier output. So what is asked? DC value. So VDC is equal to Vm by pi it is. Which is 5 volts by pi it is. So whatever the answer is. Must be 1.5 I think. Done? Perfect. Nitish, I didn't understand what is X. What is X there? Satyasri, done. Very good. This, can I give it as homework, guys? After doing these many questions? The ratio of VRMS and VDC at the output of the rectifier is. That means ripple factor it is, right? It is nothing but ripple factor. Come on. You can take this as homework, guys. Same way, it is 10 sin omega t, positive, negative. What are the diodes forward bias and what is the output? Draw the output waveform and then find the average value, RMS value, whatever. Then you will get the ratio. Okay? Call it as D1, D2, D3, D4. Here there is no connection, this is just overlapping only. Okay? Assume like that. So during positive half cycle, this is forward bias, this is reverse bias, this is reverse bias, this is forward bias. So how the current flows? Current flows like this. So this is how the current direction, positive waveform. Any division of current is happening? No. So that means full waveform you will get. During negative half cycle, how it is? Negative. During negative half cycle, this diode is forward bias, this is reverse bias, this is reverse bias because it is negative. So this is how the direction of the current is. Yeah, both the times the current is flowing in the same direction. So it is like a bridge rectifier it is. And in fact it is a bridge rectifier. So the waveform you are getting is same as input positive half cycles. So 10. So you can find what is the average value, you can find what is the RMS value and take the ratio, you will get the answer. I think it must be 1.11, isn't it? It should be 1.11, isn't it? Bridge rectifier ripple factor is 1.11. Yeah, bridge rectifier 1 point. VRMS by VDC is form factor, sorry, it is form factor. VRMS by VDC is form factor. Yeah, sorry. This is not ripple factor, it is form factor. The ratio of this is form factor. Done, guys. Now come to the regulators. Another very important topic it is. Regulator is very important. I'll just give you one equation in this. With that you can find very simply all the answers of regulators. Only 3 points to remember and an equation. Then any regulator you can work on. First of all, let's see what is regulator. What is regulator? The name itself tells you regulator is a circuit which maintains the output voltage constant irrespective of the variations in input and variations in load, both. This is input, this is load. If load increases or decreases, if input increases or decreases, output voltage will be constant. That is what regulator is. Simple way regulator is. But remember, what is regulator? Regulator is a circuit. Remember, it is a circuit. It is not a device which contains a diode, which consists of a diode. What diode? Zener diode. Zener diode will behave like a regulator, provided there are some conditions applied. Star mark. Zener diode just like that will not behave like a regulator. Yeah. Abid is asking check Zener. Zener, what should I check? Okay. So how this is? I'll show you. This is a symbolic representation of the Zener diode. This is anode and cathode. Equivalently, we represent Zener diode as VZ here like this, but again I told you with a condition applied. What is that condition? Zener diode if I have this Zener diode like this is very important. All of you please make a note of this. If you know this, then one equation I'll give you, rest all things will become easy. Zener can be operated in 3 regions of operation. One is forward bias, another is reverse bias, like a normal diode. Like normal forward bias, Zener also can be forward bias. Like a normal diode, Zener also can be reverse bias. But the another and special is breakdown. Breakdown region. Zener can also be operated in breakdown region. So Zener has 3 regions of operation: forward bias, reverse bias, which are not special and something interesting for us. The only speciality of Zener diode is under breakdown region. So I'm not going to tell you what is breakdown here, okay? How breakdown occurs, all those things I'm not going to tell you. What is forward bias? Simply anode voltage greater than cathode voltage is forward bias. What is reverse bias? Cathode voltage is greater than anode voltage is reverse bias, or anode voltage is less than cathode voltage is reverse bias. What is breakdown? This is very important. What is breakdown? Cathode voltage of the Zener greater than anode obviously, but should also be greater than a particular voltage called as Zener voltage, Zener breakdown voltage. This is called Zener breakdown voltage, and whose value, Zener breakdown voltage, will be different for different Zener diodes. That means different Zener diodes with different breakdowns are available in the market. You can buy like different resistors available with different values, different capacitors available with different values, different Zener diodes are available with different breakdown voltages. Okay, suppose if you want to have Zener diode with breakdown voltage of 5 volts, you can get it, or close to 5 volts you can get it, something like that. Suppose if you know a Zener diode whose breakdown voltage Vz is equal to 5 volts, then if you want to operate this under breakdown region, then the cathode voltage you need to apply, you have to ensure, you have to make sure that the voltage what you apply at the cathode should be greater than 5 volts, so that it is in breakdown region. Okay, this is what. So if this is, let's say it is 5 volts Zener diode, then the voltage here must be greater than anode by 5 volts. Let's say anode is connected to ground, cathode should be greater than 5 volts, so that the voltage across the Zener is constant at 5 volts. Under breakdown voltage, remember this one, voltage across the Zener is constant and is equal to Vz. That's what important is. That is why it is shown with a battery like this. This is ideal case. Zener diode can be represented as a battery, but there is no battery inside the Zener diode. Some students asked me later, some time back, that how Zener is having a battery inside. No, it is not having a battery inside. It behaves like constant voltage, where battery is also like a constant voltage source, na? That's why it is. But provided if it is under breakdown region. If this is not under breakdown, it is just like open circuit or short circuit like a normal diode. Okay, this is first point. So second point is, I'll write it here. First point is, Zener should be under breakdown. Or first point, let me write Zener should be under breakdown. Or before this we can say Zener should be reverse bias also, because without reverse bias it cannot be breakdown. So I am not talking about it is under reverse bias. Okay, obviously breakdown happens under reverse bias only. Generally there is a question and discussion happened recently with some students or someone else, that Zener is operated as a regulator in reverse bias, in forward bias, none of the above. None of the above is correct. It is not operated as regulator in reverse bias. because it is operated as a regulator in breakdown only, not in reverse bias. Reverse bias, it is like open circuit only. Speciality now comes is once the GNR is under breakdown, the voltage across it is equal to Vz. Voltage across the GNR is Vz. The third important point is current flowing through the GNR is Iz. This is something interesting, guys. This is something interesting. Why? When a normal diode is under reverse bias, there is no current, na? Current is zero. But GNR is under reverse bias, current is still zero. But once breakdown occurs, current is not zero, current flows something. It's not small value. It will be like in forward bias. Large current flows. How much is that current? This current can be somewhere knee current to maximum current. This knee current also can be called as minimum current. This current can be minimum or can be maximum. The minimum current flowing through the GNR when it is under breakdown is called as knee current, and maximum current is, the current should not exceed more than that. If it is flowing more than that, GNR also gets damaged. Like normal forward bias diode also gets damaged when it is exceeding a rating. Similarly here. So that's why you have to make sure when GNR is under breakdown, voltage across the GNR is equal to the GNR voltage, GNR breakdown voltage, and the current may be somewhere in between Iz knee to Iz max, or I can call it as Iz knee to Iz max. Iz knee to Iz max. So that is more important. Here I'll show you that. So there is a current flowing here called as Iz under breakdown region. So this is the region of operation, very important. This is what breakdown region is. This is what reverse bias is. This is what under forward bias is. Like this, the curve will be, no, this is forward bias. We are not interested in this and this because normal diode is also there. We are interested in this, in which this current minimum after this breakdown, this is Vz. This is called breakdown voltage. This minimum current is called as Iz knee, and this current maximum somewhere here is called as Iz max, and we should make sure that the GNR is operated always between Iz knee to Iz max. Understood, guys? These are the three important points you have to make sure. If these are not satisfied, then this circuit using GNR is not a regulator. Remember, if you see a GNR diode, it is not necessarily be always a regulator. GNR can be used in some other way also. But of course, we prefer GNR as a regulator. But if you want to use the GNR as a regulator, these three must be satisfied. Otherwise, it cannot be as a regulator. Okay? Iz from K to A, yes, Nirmal. GNR current flows from cathode to anode. It is like reverse bias current, but not small, large. Current flows from cathode to anode. That is a specialty, in fact. Otherwise, GNR diode is nothing special. Okay. Now let's see the basic regulator circuit. This is the basic regulator circuit, how it works. As I told you, I'll tell you one basic equation. From that, any circuit can be solved. Understood. Solved and understood. Okay. Lallu is asking, Hindi में बोलो sir. बताओ क्या बताना है हिंदी में. Explanation can be, because I cannot call GNR in Hindi some other way. GNR is GNR always. Current is current. Hope you will understand, Lallu. लल्लू प्रसाद यादव. समझ में आ रहा है? मैं हिंदी में भी बोल सकता हूं, लेकिन उतना अच्छा नहीं है मेरा हिंदी उतना अच्छा नहीं है. आप हिंदी में बात कर लो, टाइप कर लो. मैं जब भी ज़रूरत है, जब भी नेसेसिटी है आपको एक्सप्लेन करने के लिए, मैं बताता हूँ. As engineering is in English, so I prefer to speak in English. Even GATE exam is also English. दोस्त ने फॉर्च्यूनर कार ले ले, लड़की पटा दे. अरे यार, why you come to this session then? You enjoy with your Fortuner, guys. Okay, come back. So here, if I want to say, all of you please remember, if I want to say this is as a regulator, if I want to say this circuit as a regulator, the first thing I need to ensure that this Zener diode is in breakdown region. That means I am assuming that the cathode voltage, what you applied here, cathode voltage is more than the VZ, breakdown voltage VZ. That is what first assumption, or we have to make sure. Okay. Second is, once it is under breakdown, you know that output voltage, this is output voltage, from here to here, this is output voltage. Output voltage from between this is equal to VZ. That is the second point. And the third is, the current flowing here is IZ. It can be minimum or maximum or in between something. How much is that something? Depends on how much is the cathode voltage. How much is the cathode voltage? Depends on how much is the VI. Okay. Current is bijli or vidyut. So I cannot say vidyut is passing through like this. थोड़ा मुश्किल है यार, आदत नहीं है. Now listen, as I told you, I'll tell you one important formula, na? This one. Let me call the current flowing here as IR. Current flowing here through the load, I call it as IL. Now the current IR is equal to IZ plus IL. This is what the current equation I wanted. Very simple and important. With this current equation, if you understand properly, regulator is gone. Regulator is so simple if you know the logic behind this equation. I'll explain how it is. Ultimately, output voltage, which is this, is equal to IL into RL, isn't it? Output voltage is IL into RL. Right? Now, how it is behaving like a regulator? How it is behaving like a regulator? Okay? Now, as I told you, if input is increased for some reason, obviously IR will increase. That increased current will go through Zener. That extra current will go through Zener because Zener is under breakdown. When it is under breakdown, the resistance offered by the Zener is very, very small. So more current flows. More the voltage here, more the breakdown voltage, less the resistance, more the current. So that extra current, whatever is coming, flowing through the Zener, so IZ increases. So when IZ increases, so current flowing IR increases, IZ increases. So what happened? That increased current is flowing through this, not to the load. So load is V0 into IL, so IL is maintained constant. For example, because of the input, let us say the current was, let me give some random example. Let's say 10 milliampere is the current. Let's say, just example, initially 10 milliampere. Out of that, let's say 4 milliampere is going through Zener, 6 milliampere is going through load, let us say. Then what is output we are getting? Output is 6 milliampere into RL. If I want to say this is as a regulator, this circuit as a regulator, then output must be constant. How it is constant? Since RL is already constant, this IL should not vary. IL should remain constant so that this into this remains constant. How it is happening? See now, if this is increasing, let us say this 10 milliampere is increased from 10 milliamperes to, let us say, it is 10 milliampere increased to 12 milliampere. That means extra 2 milliampere is coming from input because of some variation. That's what regulator is needed. If that extra 2 milliamperes is coming, that 2 milliamperes will go through Zener because Zener allows more and more current. It is in breakdown. It allows more currents. If it comes, more current is allowed because Zener is under breakdown. If it is not in breakdown, not allowed. So this 4 milliamperes will now become to 6 milliampere because more current is flowing. So how much is the load current? Remained as 6 milliampere only. So sum of these two must be equal to IR. That's what the current equation tells you. So load current remains 6 milliampere only. So output is constant. Suppose if it is increased further, let's say it is 14 milliampere. Then this becomes 8 milliampere. This becomes same 6 milliamperes. 6 plus 8 is 14 milliamperes. So output is regulated like this. What if input is reduced, sir? If input is reduced, let's say to 8 milliampere, then Zener voltage is also reduced, na? It is proportional to the input. Then what happens? Zener current also reduces to maybe let's say 2 milliampere. Just for explanation, I am taking standard values, but it is accordingly. Even milliamperes also. If it is 2 milliamperes, it is 6 milliamperes still maintained. So total is 6 plus 2 is 8. So output is still constant. So for the variations in the input, the current through the Zener is varied, not the load current. Load current remains constant. Is it okay if current through the Zener increases or decreases randomly like this? It's okay, because where it is going to the ground. It is like drainage. It's going to the ground. Our intention is to maintain the current here constant. So that is happening because of the Zener, and it allows the current maximum and minimum. And it happens only when it is under breakdown. So if you know this equation, it is mostly possible for you to solve most of the regulator problems. Okay? Clear, guys? Similar explanation I can give it for RL variation also. See, output is IL into RL. Now what if RL increases? If load increases, what? To maintain output voltage constant, IL has to decrease. How it is possible? Zener current will increase. Let's say this is 10 milliampere again, 4 milliampere and 6 milliampere. If now RL increases, then this current will decrease to 4 milliamperes, where that extra 2 milliampere will go to Zener. So the total is 10 only. This is 6 and this is 4. So variations in RL, variations in VI are compensated through the Zener current, maintaining output constant. That's why it's called as regulator. Hope you understand, guys. This explanation is very, very simple and easy. But provided Zener must be in breakdown region, output voltage equal to Vz, and the current flowing through Zener is Iz. It can be minimum, maximum, or whatever. Find the currents. Now it is very simple for you. Find the currents. Find the currents. Iz, etc., etc., etc. Find the currents now. Current through resistor R is IR. You can name them differently also. I just named as per that. This current is IL, this current is Iz. You want these currents, right? So I just told you IR is equal to Iz plus IL. From this you can find all the currents I told you. You can find. Now you can say output is equal to how much? Since it is a regulator, output is 5 volts. That means the voltage here is 5 volts. This is 5 volts. That means this is also 5 volts. Now what you want? IR you want. What is this voltage? This voltage is 12 volts. So what is IR? IR is 12 minus 5 divided by 1K. That's it. 8 milliamperes. Isn't it? 7 or 8? 12 minus 5, na? I forgot even these things. Come on, guys, are you there? IR is 12 minus 5 is 7 milliampere. 3 plus 2 is 7. Next, what is required? IL. IL. What is IL? Current flowing through this, which is nothing but 5 minus 0 by RL. RL is given 1K, which is 5 milliampere. Now what we want? IZ. IZ is what? This minus this. IR minus IL, which is 7 minus 5 is 2 milliampere. That's it. What if I increase this to 15 volts, guys? Come on. You tell me, what is this now? Come on, guys, if I increase this to 15, just tell me what is IL. IL is 5 milliampere now at 12 volts input. What is IL when it is increased to 15 volts? Five milliampere, right? What if it is increased to 20 volts? IL, I want IL. Forget about what is IZ and etc. Same, na? This is what I want. See, when input is increasing 12 to 20, but still load current is maintained constant. You tell me what is IZ? In this case, IZ is what? 2 milliampere. In this case, how much is IZ? How much is IZ? Must be more than 2 milliamperes. IZ increases in this case. You can check it, guys. 2 milliampere. Here it is 15 minus 5, 10. 10 minus how much it is? 5. So 5 milliampere. And here 20 minus 5 means 15 milliampere minus 5 is 10 milliampere. Right? 2, 5, 10. See, as this input voltage keep on increasing, that's what I told you, no? Zener current also keep on increases. Zener current increases, but load current constant. So output constant. That is how the output is constant. Then for the circuit shown, Zener current is 3 milliamperes. This is 3 milliampere. Maximum Zener current is 100. This is IZ max. What is the minimum allowable value of RL? RL minimum is required. How much is RL minimum? This is IL. This is V0 divided by IL. RL minimum you want, so IL should be maximum. So you just need to find what is IL max, because V0 is equal to VZ divided by IL maximum. VZ is given already. Come on. Make it faster. Come on, make it faster. Come on, give me the answer, guys. Yeah, Raghuram is saying 33 ohms. What about others? Should be simple, it is. Current here is IR. We want IL max, right? IL max is equal to IR minus IZ minimum. If Zener current is minimum, then IL will be maximum. What is IR? 20 minus Zener is 3.3 divided by 1K minus IZ minimum is 3 milliampere. This is IL max. That value you substitute here, where VZ is also known, IL max is also known. So you will get RL. So minimum value of RL required so that this circuit behaves like a regulator is 33 ohm, as you are saying. If the calculations are correct, 33 ohm must be correct. Come on. My video is looping. Payash Kumari. Raghuram is saying 240, guys. Others, please check it. Payash Kumar, please refresh the video once again. Yeah, it should be 240, guys. Check it, guys. It is 240 ohms. Minimum 240 ohms. Good. So I'll take it as homework for you. Okay. Input can vary from 22 to 28 volts. The Zener shown in VZ is 18 volts so long as Zener current is maintained between, this is 18 volts. Zener current is between 200 milliamperes to 2 amperes. So what should be the value? This time R is asked. So what is this? Very simple it is, right? So if you want what is R, which is nothing but Vi minus this voltage is 18 divided by the current IR. So Vi is either 22 or 28. IR you can find based on the Zener current and load current. IR you can find from this, right? IR is equal to IZ plus IL. IZ value is also given 200 milliampere or 2 amperes. So if input you are taking this, then this is the IZ. If input you are taking this, this should be the IZ. So that gives you the answer. This also I can give it as homework. We are running short of time, guys. Make it faster. Make it faster. Take it as homework and I'll respond if you need the solution and if you are not getting the answer. Take the screenshot and you can solve it later. If you don't get, you can ask me anytime. Okay. But you must get it. At this point of time, you must get it. It's a very simple problem. And this is also I am giving homework, but this is very important, guys. Very important problem. Please make it as a important problem. Note it as an important problem. This is very important. Hemant Krishna, power rating I knew is minimum or maximum. See, that's the question here to understand. Find the minimum power rating of the Zener diode in milliwatts. How much is the minimum power rating required for the Zener diode? See, if I connect this Zener diode, it should function. What should be the minimum rating of the Zener diode so that it will not damage? That's the question. So that means how much is the maximum power dissipation possible across these two terminals? Across these two terminals, if you can find, that will be the minimum rating of the Zener. That is the minimum capacity of the Zener to be connected. If I know what should be my capacity, what should be my minimum capacity to handle, I should know how much is that value is, right? How much is that highest value? If I know, for example, I am telling you, if I know that I have to take the class for 4.5 hours, then I'll check whether I can handle 4.5 hours class or not. That's what my capacity. If I have 8 hours capacity, then I am fit for that class. If I have 2 hours capacity, I am not fit for that class. So if you want to know what is the minimum rating of the Zener to be connected here, you must know what is the maximum power rating of the Zener available there. So you need to find VZ into IZ max. This is the PZ, power dissipation across the Zener maximum possible. That should be the minimum rating required for the Zener. That is the minimum rating for the Zener required. Hope you understand. 250 milliwatts is correct answer. This I told you it is very important. Please make a note of this. If you get this answer, then it's very simple. You can answer any regulator question. If you can answer this question, guys, you can answer any regulator question. It's a 2-level regulator question actually. I don't want to give even a clue for this. Please do it. If you don't get, you can reach out to me. I think you can reach out to me at this email. If you don't get this, if you get it, well and good. Yes, now entering into another interesting topic, it is BJT biasing and stabilization. Are you guys ready? We have completed diode circuits well. Just 15 minutes we are delayed. Yeah, well, we are on time almost. Good it is. Yes, guys, are you ready? Let's do it faster. BJT biasing and stabilization quickly. Okay. Here we are going to discuss what is biasing for BJT and what is stabilization required for BJT. And I am not going to explain how BJT works and all those things. That will be again in EDC part, not here. So this is a symbol for the BJT. Everyone knows. This is a constructional diagram. This is collector. This is base. This is emitter. This is N, P, N could be, or it can be PNP also, PNP. So equivalently, the BJT can be represented as back-to-back connection of two diodes, but physically you cannot connect two diodes back-to-back and try to use it as a BJT. It will not function. Just for understanding, we can assume that BJT is like a back-to-back connection of two diodes. BJT is a three-terminal device having two junctions, emitter junction and collector junction. This is emitter junction, we call it as JE, and this is called JC. And the voltage between these two is called as VBE, base to emitter voltage, and the voltage between these two is called as VBC. And the voltage between this and this is called as VCE, collector to emitter voltage. These are the three junction voltages, three terminals, and three regions of a BJT. So BJT is a three terminal, two junction, three region device. Yeah, mostly we use NPN only because of slight advantage over PNP. That is, NPN uses majority carriers as electrons, where mobility of electrons is higher than holes. But it doesn't mean that always NPN. In some special cases, wherever it is required, we go for even PNP as well. Both are important. But if you understand NPN, it is exactly same. Whatever all the points we discuss for NPN are equally valid for PNP, except in place of electrons, it is holes, and the polarities of the batteries may be slightly different. Yeah. So as I just told you, it has two junctions. This is emitter junction, this is collector junction, and three terminals. So we have four regions of operations possible. This junction doesn't mean that it is something different. It is same like normal PN junction it is. BJT junction is also exactly the same way as normal PN junction. The only difference is the dopings. The emitter here, right? This is base here and this is collector. The dopings are slightly different here. This is heavily doped N++, and base is moderately doped as P+, we represent as. Collector is lightly doped and we represent as N. So they are not equally doped, and the size of these regions are also not same. They are different sizes. Collector is highest size, emitter is next, base is as thin as possible. These are the constructional details about the BJT. Now my interest point is how we can operate and what are the regions of operation for BJT. There are four regions of operations based on JE and JC, how you operate. So we can reverse bias this and we can reverse bias this. So this is what we call it as cutoff. In VC, cutoff VCE voltage across collector and emitter is highest. So it is highest, and IC is 0. So application is like open circuit switch. Okay. Less in NPN, no, not necessarily, Ashok. Power consumption, not in that point of view. So this can be forward bias. This can be also forward bias. This is called saturation. Two junctions are forward bias is called saturation. Here it is close to 0. Here it is IC is highest. or maximum, let me write it as maximum or minimum. So let me write it here, it is maximum, voltage is maximum when it is in cutoff, current is maximum when it is in saturation. This is like short circuit, like normal diode short circuit. So between cutoff and saturation, it is like a switch. So BJT can be operated as a switch between saturation and cutoff. And then most important is emitter junction forward bias, collector junction reverse bias. This is active region. Active region. Here it is some value. Here it is some value, not zero or maximum. This is as an amplifier. This is very important. If you want to use the BJT as an amplifier, you have to operate the BJT in active region by making emitter junction forward bias, collector junction reverse bias. The last region of operation is reverse to the active region. That's why it is called reverse active region. Reverse active region it is. So here it is also some values, but it is not used as an amplifier. It is generally used as attenuator there. Okay. Thanks, Lallu. Nirmal Kumar, saturation it is close to 0.2 for practical diode. Ideally it is 0. Practically for silicon transistor it is 0.2, for germanium it is 0.1. But ideally it is close to 0 or yeah. Saturation VC is less than 0.2 or 0.1, close to. Okay, these are the reasons of operation. But out of all these, my importance is always with this. This is most important for us. Why? Because no other device can be as amplifier except BJT, that too in active region. So amplification is possible only with BJT, not with any other device except MOSFET and FET. Okay, diodes, resistors, capacitors cannot be used as amplifiers except the transistor. The transistor can be BJT. But if you want BJT as an amplifier, you have to operate this in active region. Remember this. Okay, done guys. So these are most important and sufficient for you, just regions of operation. So one shortcut I want to give you about region of operation. If you want to directly find out how the region of operation or what the region of operation is, you just concentrate on VBE value and VBC value. I told you already what is VBE, VBC. So this is VBE, this is VBC. You just try to find what these values are, and then you can easily find out the region of operation. This is a shortcut and technique, because this is also very important. So if both are positive is called as saturation, opposite to that is cutoff, both are negative, cutoff, and this is active region. VBE is positive, VBC is negative, and opposite to that is inverse active region or reverse active region. It's as simple as that. So if you don't know whether BJT is operated in active region, saturation or cutoff, etc., etc., you just need to find the junction voltages, and according to this coordinate method, you can easily identify whether BJT is saturation or cutoff or active or inverse. This is just a trick and shortcut. Okay. Now based on this, I think you can find what is the region of operation. Come on guys, quickly, what is the region of operation? So whether this transistor is in cutoff or saturation or active. So just find VBE and VBC. This is VBE, this is VBC. So how much is VBE? Which is nothing but VB minus VE, isn't it? VB minus VE. So 3 minus 1, it is equal to 2 volts. So what is VBC? It is 3 minus 5. So it is VB minus VC. So it is minus 2. So VB is positive, VBC is negative. So what is the region of operation? You can check. VB is positive, VBC is negative. So the transistor is in active region. So the transistor is in active region. Like that you can find. Yeah, Raghuram is C. Similarly, other circuits guys. Here it is negative. So minus 3, this is minus 3. Minus 3 minus 0 is negative. Okay. Minus 3 minus 5 is again negative. Negative, negative means transistor is in cutoff. Both are negative means cutoff. Okay. Similarly, other circuits you can easily now do is, this is positive here, and this is 2 minus of minus 3 positive here. Both are positive, positive. That means it is saturation here. Isn't it? This you can check it, guys. But be careful, this is JE. This is JE and this is JC here. Just to confuse you. So base to emitter VBE. Base is at -2, -2 minus of minus is +5. So it is positive. And here it is collector junction is base to collector, -2 to 0. Minus, that means negative it is. Positive, negative, that means active region. It is active. It is active. Guys, this is active. So these are different ways of keeping it active region. Okay. Now coming to the operating point. Operating point is very simple, nothing but at what voltage and current, DC voltage and current, at what DC voltage and current, operating point is at what DC voltage and current you are operating the transistor, BJT. So operating point is nothing but what is the value of VCE you are operating and what is the value of IC you are operating. That's called operating point. It is generally denoted with the Q. Q-send point. We also call it as Q-send point. Q-send point. It is also called as bias point. Also called as operating point or Q point. All are same. Suppose if this value is 0 and this value is highest, then the transistor is operated in saturation. If this value is highest and this value is 0, that means this transistor is operated in cutoff. Neither this nor this are 0. That is active region. So at what value of VC and IC you are operating is called as operating point. We don't give more importance to saturation and cutoff because we want to use the BJT as an amplifier. That is a unique speciality of BJT. So we want to operate the transistor in active region, right? That's what we said, no? So the value of VC and IC should not be equal to 0. Any value should not be equal to 0. That's what active region is. So how we find that? To find what is that operating point value VC and IC, this is the axis of VCE will take. This is the IC axis will take. Okay. How to find how much is the value of VC and IC. Okay. So we'll find, I'll tell you the method how to find. We'll find highest value of VCE. We find highest value of IC. We join these 2 points. We'll get a line and this line we call it as load line or DC load line because it is drawn for DC values. And any point on this line is an operating point. Any point on this line is an operating point. Then what should be our preference? Any point you can take because any point, for example, this point if I take corresponds to this voltage, this becomes VCE and this becomes IC, non-zero values. That's what operating point and active region. So any point on this line is active region. And this point is cutoff and this point is saturation. Any point between cutoff and saturation is active region. Is that clear? Right? Yeah. So now if so many points are operating points, what point we have to operate? Always remember we have to prefer the center point. How to find the center point? Take the center point like this. Take the center point like this. So this center point should be the preferred value, not compulsory, it is preferred. So operating point in general we mean any value of VC and IC, but preferably we go with center of the DC load line, which gives highest amplification. Ultimately, we are going to operate the transistor with this value of VCE and with this value of IC. How and what for? To use it as an amplifier. If you do so, you will get highest amplification. That is why we want this transistor to be operated in center of the DC load line. Understood? Right. Now, stability factor. So, what is the stability factor and what is its importance? As we just discussed, operating point is to be operated at the center, right? Operating point is This one, it is preferred. This value of VC, this is IC and this is VC. This is preferred. And this operating point, what is the guarantee that it will remain there only? It is sensitive to the temperature. It changes with respect to temperature. It changes with respect to beta. It changes with respect to VBE value. If temperature increases, operating point may change. So we need to ensure that this operating point will not change with respect to temperature, beta or VBE. Making sure that the operating point is not changing is called maintaining the stability in the operating point, and the factor which defines whether operating point is stable or not is called as stability factor and is denoted with S, capital S. So it is also important that if you are operating the transistor, you have to make sure that it is in active region. You have to operate certain value of VC and IC. You have to make sure that those values even constant, even if temperature is changing and other parameters of the BJT are changing. Once all these things are done, then the transistor is perfectly biased. Biased for what? Biased for using it as an amplifier. Then you can apply the signal and get the amplification. Hope it is clear, guys. Done? Let's move on now. BJT biasing methods. Then what is biasing? As I just told you, biasing is nothing but applying DC voltage and current, right? That is what, nothing but operating point, maintaining operating point. What is that? VCE value and IC value. How much? At the center of the DC load line. To provide that value of VC and IC, we need different circuits. So those are the circuits which provide the necessary biasing. Biasing is nothing but operating point, are called biasing circuits. So different biasing methods, circuits. One of them is fixed bias circuit. So here I am not going to explain how the fixed bias circuit works and all, because you must be knowing it already. Yeah. Very good. BYJU'S exam prep people are congratulating and clapping you and giving the correct answers and responding. Come on, guys, keep responding, keep getting appreciation. So my point here is very important, that because ultimately you have to answer gate questions, right? So of course this circuit provides biasing. This is the DC voltage what we provide, and this gives you some voltage between base and emitter, and this gives you some voltage between base and collector, and this gives you some voltage between collector and emitter. These are the junction voltages. So this terminal we call it as base terminal, and the voltage we call it as VB, and this terminal is VC, and this terminal is VE. And the current flowing here is IB, we call it as, current flowing here is IC, we call it as. Sum of these two currents is IE. Emitter current is always sum of base and emitter current. This is all we know. Ravi Teja, that's what I am going to tell you. How to find the values of VC and IC, right? That's what I am going to tell you. That is what even in the gate examination also they'll ask. In the gate, that's what I'm going to tell you. In the fixed bias circuit, I'm not going to explain how it works and all those things. In the examination, what they'll ask? They'll ask how to find what is IC. What is the value of IC they'll ask. Or what is the value of VC they ask. Or what is the value of VB they ask. Or what is the value of IB they ask. Etc. etc. They ask anything, or they'll give the current values and ask the resistor value, etc. Parmit, yes. Pramit Banerjee, yes, you need to remember the formula for stability factor. Yes, you have to remember. So I'll give you anyhow here also, if time permits, the stability factor values. If not, just you can see our content anywhere. Many times we have given circulated this content, there it is available. Even in our app also, in the material it is available. But it is good if you can by heart these formulas always. Now, what I am saying, yeah. So to find these currents or voltage, whatever is asked, what is the method? So again, I am telling you three simple things, 3-step method I am telling you, so that you can find anything, whatever they asked in the examination. So let me tell you what are they. Ultimately, what you have to do is, the first thing you have to do is apply KVL in base loop. Base loop. What is base loop? This one. This is a loop now. You apply the KVL in the base loop so that you can find what is IB. Okay. Once IB is found, you can find what is IC, because IC is equal to beta times of IB. Then third step is find what is VC. Because IC is known, VC is nothing but VCC minus the drop across this. You can find, apply KVL and you can find it. Once you get IC and VC, here in this case VC is nothing but VC, which is also nothing but VC, because emitter voltage is 0. VC is nothing but VC minus VE, emitter is 0, so VC is equal to VC. So you got what is VC and you got what is IC. That's what the Q point is. That's what Q point or operating point is. Done. Isn't it? As simple as that. Right? Any circuit you find like this, any fixed bias circuit, try first applying the KVL in the base loop, find IB, then IC, then VC, and rest all can be found. Suppose if VB is required, this is required. What is this? VCC minus the drop across this. So it is nothing but VCC minus IB into RB. These values will be given. So IB you found it already. So you get the answer. So simple, these three steps, even for other circuits also. Let's go with another one. There is another circuit called collector to base bias. This is another method. This is also called as feedback resistor method. This is another method. Why? Because fixed bias has some problem. What is that problem? Stability problem. Fixed bias is not stable with respect to temperature. So that's why stability factor equal to 1 plus beta for fixed bias. So if beta is large taken for the transistor, then stability factor is large. Stability factor large means operating point is not stable. Stability factor close to 1 is stable. S is close to 1. Stability factor close to 1 is ideal. Stability factor close to 1 is preferred. Stability factor large is not a good biasing circuit, because biasing circuit has to provide biasing as well as stability. So in a fixed bias circuit, the stability factor is S is equal to 1 plus beta. You will get 1 plus beta, which is very large. Beta is very large, so stability factor is large. So that should be close to 1. That's not possible. That's why we want another circuit called as collector to base bias. Again, I don't want to go for explanation of this, but we are interested in finding what is IC, what is IB, what is IE, so that we can find all the currents and voltage. This is VC, this is VB, VE is 0, anything you can find. But again, what is the method? Apply KVL. Apply KVL in base loop. Same method. So what is base loop? This one. So how the base loop current equation is? KVL is VCC minus IB plus IC into RC minus IB into RB minus VBE is equal to 0. From this you can find what is IB. Easily you can find, right? So the current flowing here is IC, the current flowing here is IB. So the current flowing here is IB plus IC. Please make a note of this. So you can find IB. Then what you have to do? Immediately go for IC. IC is beta times of IB. Third, whatever the voltage you want, you can find. In fact, it is two-step method. Directly we can get. The stability factor for this, S is equal to 1 plus beta by 1 minus 1 plus RC by RC plus RB. Is this? Yes, this will be the stability factor equation for the collector to base bias. You have to remember this equation. Here, if you want this close to 1, you want this close to 1, then RC should be far greater than RB. This is the condition for getting stability factor close to 1. If RC is far greater than RB, RB can be neglected, this becomes, sorry, I think I have written something wrong. 1 plus beta by 1 minus, this is, if it is neglected 1 it is, 1 by 1 is, sorry, this is beta into 1 plus beta into RC by RC plus RB. This is the formula. 1 plus beta by 1 plus beta into RC by RC plus RB. If RC is far greater than RB, this term can be taken as RC. RC by RC is 1. 1 plus beta by 1 plus beta is 1. So this should be the stability factor for this. But the problem here with this is this condition. This condition is not possible practically to take RC higher than, yeah, beta times, yes, beta times RC by Krishnaveni, correct. Okay. So with this problem, that this is the condition is the problem. That's why we go with another circuit called potential divider bias or cell bias circuit. Potential divider or cell bias. Here again I'll tell you a simple method. Two methods I'll tell you. One is exact method and another is simplified method. So what is exact method is, whenever you see potential divider bias, you please replace this with the Thevenin's equivalent circuit at the base. 1 plus 1 minus beta times dIB by DIC. Yes, Nirmal. dIB by DIC, if you find, it becomes minus RC by RC plus RB. So if you substitute that, this is the equation comes to. This is the equation comes to. Okay. Potential divider bias. Whenever you see a potential divider bias, to find the currents and voltages, what you have to do is you have to replace the base circuit with the Thevenin's equivalent. I am not going to tell you how the Thevenin's equivalent, all those things, because it takes a lot of time. So how the circuit can be replaced? Thevenin's voltage, Thevenin's resistance, like this. This is VTH and this is RTH. And then remaining circuit. What is remaining circuit? Transistor as it is, emitter, collector, RC. This is VCC as usual. This is RE as usual. This is connected to ground. This is connected to ground. Done. This is how, where VTH is what? V Thevenin's voltage is equal to VCC into R2 upon R1 plus R2. If you don't know how to find it, just by heart it, that's also okay. R Thevenin's is equal to R1 R2 by R1 plus R2. If you don't know how to find Thevenin's and Thevenin's voltage and resistance, then just by heart this, sufficient. Kranti, frequency response. I am going to explain Kranti. Just wait for another 15 minutes. We will come to frequency response as well. Once I finish amplifiers, I will tell you what is frequency response. Okay? Yes. Now this becomes simple. Then from here onwards, what you have to do is, from here onwards, it is again step 1, step 2, step 3. Apply KVL here. Again, KVL in the base loop. Then find IB, then find IC, find rest of the things. Yeah, stability factor here is, I'll tell you the stability factor equation also. Stability factor is equal to 1 plus beta by 1 plus beta into RE upon RE plus R Thevenin's is the stability factor equation here. So to make this stability factor close to 1, to stabilize the operating point, we need to choose this value of resistor far greater than, RE should be far greater than R Thevenin's, where R Thevenin's is this. If you choose the resistors like this, Kirtana, when you apply Thevenin's theorem, open circuit this, you will get the Thevenin's voltage, short circuit this, you will get the Thevenin's resistance. Okay, Kirtana? That is how the Thevenin's theorem states. According to the Thevenin's theorem, open circuit voltage and short circuit resistance gives you Thevenin's voltage and Thevenin's resistance. So that is the condition. And this is, remember, most important biasing, because this is the best biasing available for. That's why most of the times you see this potential divider bias always, most of the cases. Any transistor amplifier, you will see potential divider for this reason. Stability is there, operating point is there, and most important is this potential divider bias not only for BJT, can be used for FET and MOS also. Yeah, another method to solve this is approximate method. This is another important method you can find. So what is this approximate method is? The name itself tells you that it is approximate. So what the approximation you have to take is, you will take IB is equal to 0. This is the approximation you are taking. This is the approximation you are taking. Okay. Since we know base current is very small, we can take it as 0. This is what assumption we are taking. That's why we call it as approximate method. Once this IB is 0 we are taking, current flowing here, this is like open circuit, right? Current is 0 means it is open. So the voltage here, we call it as VB. VB is equal to VCC into R2 upon R1 plus R2 it becomes. So this is point number 1, this is point number 2. Point number 3 is VE is equal to VB minus VBE, which is known. This is known already. So VE you find VE, this is VE. And the fourth step is, once you know VE, you can find IE. IE is equal to VE by RE. You will get IE. Once IE get, then you can find what is IB, which is IE by 1 plus beta. You can get IC, beta times of IB. So this gives no Thevenin's theorem is required. So as I just used Thevenin's theorem, many students got many questions that how this is, how that is. So if you are not familiar with Thevenin's voltage or Thevenin's resistance, then simply go for this approximate method. You will get the answers almost same. Only condition is you have to have beta very large for this. You have to have beta of the transistor very large to make this approximate close to the exact. So this way you have to find this. Once you got the currents, any voltage you can find easily. Okay, large beta, yes. Clear now guys? One more thing is emitter bias. One more biasing circuit method is emitter bias. In fact, for BJT, emitter bias is better. For this also again same, KVL in the base loop, then find IB, then IE, then IC. This is nothing special. So it is similar to the fixed bias, but the only thing is this will provide biasing as well as stability also here. It is like fixed bias, it is not fixed bias. It is similar to the fixed bias, will not have this. This will have. Okay. Right, this is what biasing is. So what is asked in the examination? It is asked to find different currents. So let me show you some examples also. But before that, there is another upcoming session, which is general aptitude session by Rakesh sir, your favorite Rakesh Salreja. And it's going to be 15 marks in 15 hours. So 15 hours of marathon on general aptitude. It's going to come soon by Rakesh sir. So you can score easily 15 marks out of 15 and makes a lot of difference. Yes, Nirmal, KVL and KCL, if you know biasing, you can play with. Easily we can play with. So another session is non-stop maths marathon session by Ankit sir and Rakesh sir again. And complete syllabus of maths in just 2 days. This is also just quick revision. You can revise all the mathematics concepts. As you know, maths plays very important role. And aptitude also plays very important role. So these two together close to 25-30 marks, not a joke. Yeah, see some examples how to find these currents. Very simple. You can quickly give the answers, guys. IC and VC is required. So find the value of IC and VC. Assume VBE value, beta value is given. So VBE is from here to here. So IB is the current flowing in the base, IB. And VC is the current voltage across this terminal. So what I told you, first step, apply KVL in the base loop. So this is the KVL you need to apply. So 20 minus IB into 200K minus VBE. VBE is given 0.7. So it is 0.7 is equal to 0. So we can find what is IB. So it is 20 minus 0.7 divided by 200K. Whatever is the answer. So what is the second step? Just find IC, which is beta times of IB. So we know already beta times of IB is found. Got it. Third step is VC. VC is nothing but what? This minus the drop across this. So it is 20 minus IC into 1K. So IC we found, so you can get the answer. Come on, give the answers, guys. Come on, guys, give. Yes, guys, those students, as our team is also saying, those students continuously staying with us from 4 p.m. non-stop, almost 4 hours it is. Constantly you people are there with us. That proves that you deserve a good rank in the GATE exam. That deserves, you guys deserve a very good performance in the GATE exam. And it is going to be true also. Those whose students will put efforts will never be cheated, will never be disappointed. So kudos to all the students, and I appreciate you all guys for your consistent efforts and patience for these long hours of revision. Yeah, career is goal. Yes, more the efforts you put, better the career, guys. It looks like you are spending a lot of time, you are taking a lot of pressure on you, but that gives you long-term results. If you work hard for this 1 year or half year, in the last 1 month, if you are putting more efforts, then this going to be helping you or resulting next 30-35 years of your career life. Right, so you got the answers. It's very simple. Okay, this way you need to just, as I told you, this is a fixed bias circuit. Just apply KVL and patience is main. Yes, 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 yes. Next, find the current IC. So again, first step is apply the KVL like this. So it is 15 volts minus IB plus IC into 1K minus IB into 200K, IB into 200K minus VBE is given 0.7 is equal to 0. So this IC you can write it as beta IB. So entire equation is in terms of IB. So IB equal to 15 minus 0.7 divided by 1 plus beta into 1K plus 200K. This is IB. Then second step is simple IC. Beta times of IB it is. Third, whatever is asked, easily found. Yes, Payash Kumari. Consistency, yes. Patience. Beta is given, guys. Beta is given 50. Persistence, consistency, patience. These are all the qualities required if you are going for any competitive exam, any goal to achieve. Not only this. Even for simple car driving to learn also, you need some patience. Instantly in 1 day or 2 days you cannot learn. You need your efforts, you need to patient, you need to be consistent, then you will get the result better. Yeah, beta equal to, so got it. See, these 3 steps what I told, the 3 simple steps what you just need to do to get the answers whatever is asked for. Then IC and VC, okay, for this beta equal to 150, VB is 0.6 given. See, be little careful here. Beta is VB is 0.6. Generally it is 0.7. Of course, the data gives you 0.6. You have to use 0.6 only. Now I am going to use approximate method, guys. Okay, I am going to use approximate method. So approximate method gives me VB here. VB. VB is what? 20 into 1K by 5K. That means 4 volts. If this is 4 volts, what is the voltage here? What is asked to find? IC, no? Easily find it. So what is this voltage? This voltage is 4 minus the drop across this. What is this? 0.6 volts given. 4 minus 0.6 is 3.4 volts. If this is 3.4 volts, what is IE? IE is equal to 3.4 volts divided by 1K is 3.4 milliamperes. So almost equal to IC. IE and IC are almost equal because IB is very small, R we neglected it. Approximate method we neglected it. So answer should be, ask for IC, na? So answer should be close to 3.4 milliamperes. Find it where it is. 3.4 milliamperes. Answer should be A. This is not correct, this is not correct, this is not correct. I don't even find what is VCE. I'll give the answer. Varun, you can go for Thevenin's method also, no doubt. You can go for Thevenin's method also. You will get exact values. I got approximate value. This is approximate value, but I am okay because answer is almost matching with this 3.37, 3.4. So I got the answer. Then why should I waste my time in applying KVL and applying Thevenin's, etc., etc.? That's why approximate method is okay. But I should make sure that beta is large or not for this to apply. Yes, beta is large, 150, more than 80, 90 is considered as large value. So you'll get the answers for that. Okay. So this you take it as homework, guys. You can take it as homework. So you just need to apply KVL in this and then rest you can proceed. So this also please take it as homework because we need to discuss many other things. Please take these problems as homework. If you don't get, I am there. But these are all very good problems. Remember, these are all good problems. If you can able to solve such questions, that means you are good at biasing part. That I am sure for. So I am skipping these problems, guys. So please take them as homework. Take the screenshots and go ahead. So this is all about finding junction voltage and applying the KVL correspondingly. This is most important problem. If you get this, that means you are perfect with biasing. So I am sure for. So take the screenshot. I'll give space and time to you. Take the screenshot and solve this. Find the value of VC, this voltage. So let me solve this. Little bigger it is, but looks very big, but it's very simple. So let me solve for you. What is VC is asked for. So VC is clearly nothing but 10 volts minus the current here. Can I call it as IC? So it is IC into 2K. So our goal is to find what is IC. Okay. So the voltage, see the base currents are 0. So I assume the base currents are 0. Approximate method I am going for. So the voltage here I call it as VB or VB1 or VB2. I am assuming this as Q1 or Q2. So I call it as VB1. So what is VB1? VB1 is equal to, when this current is 0, this current is 0, it is like 3 resistors in series. So voltage division formula. So VB1 is 10 volts into 1K resistor divided by all these 3 resistors, 2.5, 7.5K. So this gives some value VB. Tell me guys, how much is that? Someone please tell me how much is that? How much is this VB1? Please tell me. Solve this and tell me. Now what is this value? I call it as VE or VE1. So VE1 will be VB1 minus VBE. How much is VBE? 0.3. You will get VB1. Then immediately I will get what is IE. This current IE I will get. Come on guys, anyone? 1.33. Very good. So this is 1.33. So this is 1 volt. VE is 1 volt. So what is IE? 1 milliampere. If IE is 1 milliampere, what is IC? it is also 1 milliampere. So what is VC? 10 minus 1 milliampere 2 is 8 volts. So the answer is 8 volts. Must be 8 volts. Clear? Like this. Very simple. The circuit looks so big, but if you apply our techniques, you will get the answer faster. Yes. Very good, guys. Very good. Yeah, current mirrors. I'll wrap it up very fast. Current mirror circuit. It is called current mirror because the current flowing here is almost equal to the current flowing here in this transistor is almost equal to the current flowing through this resistor R1 is equal to I1. That's why it is called current mirror. It is the mirror image. The current here is the mirror image of this current. That's why it is called current mirror. Suppose if it is 1 milliampere, then the current here also is almost equal to 1 milliampere. Okay? That type of circuits are called as current mirrors. But again, no one is going to ask you how the explanation is in the gate examination. They will ask you how to find the currents. Again, since it is a revision session, it is a quick revision session. I am going to give you a method only. Explanation, if you have time, we can discuss that. So let me explain how it. But I have to give you what is I1 equation. I1 is you can find by applying KVL like this. This is a loop now. You can apply KVL like this so that you can find what is I1. So I1 I can apply it as applying a KVL. First let me apply KVL and I can extract what is I1 so that it will not be confusing. So it is 0 minus I1 into R1 minus, after this is the VBE, minus VBE, minus of minus VEE is plus VEE. Plus VEE is equal to 0. So what I want? I1. So I1 is equal to, if I take that other side, VEE minus VBE divided by R1. So this is how I1, whose value is almost equal to IC1. IC1 or IC2. So I can say it is IC2. IC2. So that is why it is called as current mirror. But the conditions here is both the transistors should be identical. What is meaning of identical? So beta 1 must be equal to beta 2. This is a condition. Second thing, this transistor must be shorted with gate and must be shorted with collector and base. If this connection is missing, this will not behave like a current mirror. Please make sure, even though circuit looks like this, if this connection is not there, this will not behave like a current mirror. So this is called current mirror, and generally this circuit is used to have as a current source in a circuit. Like for example, in differential amplifier, at the emitter you want the current as a source. So we use this type of current mirrors there, even in op amp circuits also. So the condition is both transistors must be identical here. That is in fact the problem with this current mirror, because it is very difficult to have the same transistor with same beta value practically. That's why we modify this. We modify this and called as modified current mirror with one more transistor. So this also needs transistors to be identical, but beta need not be large. Here the transistor should be identical and beta should be large to have this value equal to this value. But whereas in this circuit even beta is small, but this current is almost equal to I1 happens. Here also I must say what is I1. Here I1 is equal to, again you can get it by applying KVL here. This is the loop now. This is a loop you can apply. So I1 is equal to, I can say it is VEE minus 2 VBE divided by R1 it is. So this resistor and this voltage decides how much is this current. Accordingly, now the current flowing here also. So if you want this current here as 1 milliampere, you need to adjust this resistor and this voltage accordingly, so that the current here will be 1 milliampere and so that the current here will be 1 milliampere. That's what the current mirror circuit is. Okay. But most important is how to find the values. So here it is asked to find the value of R. This resistor is asked to find. So very simple it is. You just need to first identify it is a current mirror circuit because this connection is there. Two transistors are connected back to back. So this current is given So this is given 1 milliampere. So immediately what you can say, this current is 1 milliampere because it is current mirror circuit. That's what the point you need to identify. Okay. KVL, KCL plays a lot of role, correct. Now once you know the current here, you want the resistor only, right? You want this resistance. So this resistance is nothing but this voltage minus this voltage by current. So what is this voltage? Nothing but this voltage. What is this voltage? Nothing but from here to ground. What is this? VBE. So what is this resistance? R is equal to 10 minus VBE divided by the current is 1 milliampere. VBE is given. So we got the answer. So 9.3 K. B is the answer. So KVL helps you a lot. But here please make a note, due to time constraint I am not explaining how this functions. But yes, we can understand how it works also, how it is equal also, all the derivations and all we can do. But it takes some time. So since we are in a hurry to revise and the exam is very near, so let's not work on how functions, how the explanation. Let us bother about how to solve. That is most important at this point of time. Yeah, it's almost Raghuram, almost like Brahmas. This you can try guys. Now you can try this. Beta is 100 for both the transistors. Find the value of VCE1. So that means the voltage from here to here, VC, and this is VE. So from here to here, how much is the voltage? That's what VCE. So for that, what you need? The current here is needed. So that current is nothing but this current. So you know how to find I1, find it. That current you take it, you will get the voltage. That's the answer. Done? Okay. Perfectly matched transistors are connected as shown. Beta is very large. Beta is very large and transistors are matched. Junction voltage is 0.7. That means VB is 0.7. Find I. That means this current is required to find. Come on guys, you can do this. Can I take it as homework then? Be careful, there is one more diode added here. Be careful. So you just need to apply KVL like this to find what is I1. That current is equal to this current. It is just reverse. Circuit is drawn differently. It is also current mirror. See, one transistor should be like this. One transistor should be connected collector and base. So it is a current mirror. So if you find what is this current, that is nothing but I1. This current is nothing but I1. That is equal to IC1. So please take it as homework. Please make a note that this is also having VBE, junction voltage. I should not call it as VBE in fact. This will have a junction voltage of 0.7 volts. And this is also having a junction voltage of 0.7 volts. So while taking the current equation, you have to be very careful. Right, done. This is about current mirrors. Now jumping on to amplifiers guys, quickly. Amplifiers. So what is an amplifier? Come on guys, you please define what is an amplifier quickly. Yes, by 8:30 we should finish this. What is an amplifier? Come on, quickly. So many students will give many definitions like amplifier is a circuit which amplifies, which increases the signal, amplifies the signal, etc. But not like that. Remember guys, example I'll tell you to understand clearly what is an amplifier. Suppose this is a signal applied. Let's say it is 10 millivolt signal. And if you get a 10 volt signal. This can be possible by step-up transformer also. Step-up transformer can give 10 millivolt signal as 10 volt signal. Sinusoidal only. If you give it this same signal 10 millivolts to amplifier, okay, then also you will get 10 volts. Then what is the difference guys? In both the cases 10 millivolts is given as 10 volts, 10 millivolts given as 10 volts. Then what is amplifier is doing? What is not step down transformer is doing or step up transformer is doing? The difference is power levels. If I find input power here and output power here, output power is exactly equal to the input power in a step-up transformer or step-down transformer. Step-up or step-down, power at the input means primary and secondary will be same. Whereas in an amplifier, output power, if I find what is input power here, is greater than input power. This happens. If output power of the signal of the circuit is higher than the input power, such circuit is called as an amplifier, otherwise no. Okay. Chinmay Roy, amplifier dedicated voltages and signals of a circuit. No, it is power levels. Output power should be greater than input power if I want to call that circuit as amplifier. How? When voltage is, after all, power is equal to voltage into current, na? In transformer, how power level remains same? If voltage is increased, current will be decreased simultaneously, so that output power remains same as input power. But whereas in amplifier, output power will be higher than input power. From where that extra power is coming from? That is what the biasing we are giving, guys. That's what the biasing. So amplifier is a circuit which is supplied that additional power in the form of DC, so that AC power is enhanced and the output power is higher than input power is possible. Otherwise, how it is possible? Isn't it? So that's why biasing is compulsory. What is the need of biasing? Is to have the output power higher than input power. That is the need of the biasing here. Hope you all guys understand, right? Kirtana, power amplifier is different. Power amplifier is also an amplifier, but why it is called power amplifier is a different concept. Now, there are three types of amplifiers, as you all know. So, common base amplifier, common emitter amplifier, common collector amplifier. This all depends on where you give the input and where you take the output. If input is at emitter, and output is at collector, this is called common base, because base is common between input and output. Common emitter, input is at base, output is at collector, and base emitter is common for both. Similarly, input is at base, output is at emitter, and collector is common, is called as common collector. Based on where you give the input, where you take the output, rest of one terminal is common for both input and output. Such amplifiers are called CB, CE, CC, out of which CE is most important practically, but in gate examination it can be asked anything. Okay. Kirtana, that's correct. Amplification, power amplification happens. Yes, understood, Kirtana. Now again, I'm not going to explain how amplification happens and what is amplifier, how it looks like, all those things. Our importance is how to analyze. In the examination, what they'll ask, in the gate examination, they'll give you an amplifier circuit and they'll ask you to find voltage gain, current gain, input resistance, etc., etc. So for that, we need some analysis tools. Okay, we need some analysis equivalent circuits. There are different methods available. One of them is RE model. RE model is one of the methods to analyze the amplifier. Analysis is nothing but what? Finding voltage gain, current gain, etc., etc. Input impedance, output, only 4 parameters are very important. Voltage gain, current gain. What this voltage gain tells you? How much voltage amplification happened. What this current gain tells you? How much current amplification happened. Because power enhancement either happens by voltage or current, or both increase. So P is equal to V into I. Either voltage increase or current increase or both increase. That's what enhancement of power is. So power amplifier is required for gate instrumentation. I think yes. Pramit, yes. Power amplifier is required for IN students. So this is one of the methods. This is one of the methods to analyze the BJT amplifiers, called as RE model, and I prefer this model is the easiest and simplest model to analyze any amplifier, BJT amplifier especially. So this is the emitter. This is for common base. Okay, as I told you, there are different types of amplifier: common base, common emitter, common collector. RE model for common base is, this is emitter, this is collector, and this is base. Common base. Base is common. So this is RE. So remember, this RE value is almost equal to 26 millivolts divided by IE. So we can find what is the value of RE from the circuit by finding what is capital IE. That means biasing current. If you know how much is biasing current, we can find what is Re. Once Re is known, rest all things we can find, because alpha will be given. IE is what we can find. Alpha IE is this current. This is IC. So IC is coming like this. IB is coming like this. These two will be as IE, leaving as this. This is what Re model we call it as. So this is collector and base. Between collector and base, transistor behaves like a current source. Remember, this is very important. Transistor behaves like a current source. Why? Because it is in active region. Remember, this is valid only when it is in active region. This is called RE model. It's not compulsory to go with only RE model. You can go for any model. So the another model available is RE model for common emitter transistor, common emitter configuration. It is similar, only the difference is input is now base, collector is output, and emitter is common. Emitter will be ground or common. So here the resistance is beta Re. So where Re stands again same, Re is equal to 26 millivolts divided by IE. It is approximately, it can be 25 millivolts only. Exactly if you want, it is Vt. In fact, eta Vt by IE it is. Eta Vt by IE it is. Okay. So since Vt value is close to 26 millivolts, we can write it as. So this is again like a current source. So this is also can be used if the transistor is used in common emitter configuration. There are other methods also, like H parameter model for active region in the transistor when it is in common emitter, because this is a base, this is collector, this is emitter. So here the terminology will be in HIE, HFE, HRE, HIE, HRE and HOE are the 4 parameters, but this is called simplified H parameter model. This is called simplified. In fact, exact H parameter model little complex. That's why I tell you RE model is the easiest and simplest for gate point of view. Better you can go with, or this can be also used. Only the difference is the terminology. Okay, there RE we need to find. Here HIE value, HFE values will be given in the data. If they are not given, it's not possible to find. Right. This is HFE, this is HIE. Other two parameters like HRE and HOE will be there in the exact H parameter model, but in simplified model, this is the easiest. Then another model is called RPi model. RPi model. Different textbooks will follow different equivalent models. That this is the equivalent representation of a BJT. In fact, BJT can be equivalently represented for our comfort and for our convenience to analyze the amplifier. So different methods can be used. Like if I want to remove the tube light from here, so I can have different tools, maybe screwdriver or maybe tester or maybe cutting plier, etc., etc. Different tools can be used. Similarly, to analyze the amplifier, these are different tools like, right? So here RPi value will be given, or you can find it. ZM value, which is called as transconductance. So if you follow this one, Millman and Hackey's, if you follow Millman and Hackey's for analog circuits, it is based on H parameter analysis. If you follow Donald Niemann, it is on this one, RPi model. Even I think Sedra Smith also follows this type of methods. So it all depends on which book, but ultimately answers will be almost same. You'll get almost same answers for all the types of analysis. So what are the guidelines you have to follow for analyzing an amplifier? Analyzing an amplifier is nothing but to find AV, AI, ZI, ZO. These are the 4 parameters generally we find. To find that, what you have to do is, we have different methods, right? RE model, RPi model, H parameter, whatever. You replace the transistor with its equivalent model, whatever the equivalent model you are convenient with. Whatever the equivalent model you are convenient with, you can go with that. There is no problem. In fact, I am convenient with RE model, so I will go with RE model. If you are convenient with RPi model, you can go with RPi model also. But answers will be almost same you will get. Almost same you will get. Then short circuit all the capacitors, because you are analyzing an amplifier, you are dealing with AC. For AC, capacitor acts as short circuit. So if you find any capacitors connected, you can treat them as short circuit. And then remove the DC sources, because you are doing AC analysis, guidelines for analyzing an amplifier. Amplifier is dealing with AC signals. So DC signals are to bias the transistor. So you can remove the DC part and you can analyze for AC, and you can find how much this one is. RPi and RE are simple and easy. Exactly. Yes. So it all depends on what type of model you want to use and how you want to use. But these are the guidelines to follow to use any amplifier analysis. Yeah, for example, this is one simple amplifier circuit called a CE amplifier circuit with fixed bias. See this RC, RB provides the biasing for this transistor, and this is the input AC signal applied to the base of the transistor. See, this is the base. So input is connected to the base. Where output is taken? Output is taken from the collector. That's why it is called common emitter. Okay, common emitter. These capacitors are to isolate the DC. You know, there is some DC voltage and current because of this. That's what biasing. To isolate the DC, this C1 and C2 are. This is the load and this is the source what we apply. Source means the signal which you want to amplify. For high frequency only capacity is shorted, right sir? So it is high frequency analysis. Initially, Raviteja, actually I have assumed that capacitors are short, but yes, as you said, they are exactly short when we deal with high frequency signals. But at low frequency signals, they also have some attenuation. They also have some reactance to offer. So we have to consider them also as per the frequency of the signal what you applied. Yeah, based on the signal frequency. Initially, I'm not talking about this. That's what if I speak about the frequency of the signal also, then the effects will be something different, because capacitors also need to be considered. Even if the high frequency is discussed, transistor junction capacitance is also to be considered. So that is what we discuss in the frequency response. Frequency response is the response of an amplifier for different frequencies of the input signal applied. That's what frequency response. We'll discuss that separately. Let's not combine this also here. Already amplifier circuit is little complex, where DC is also there and AC is also there. So it is little complex. If we add up frequency component also in this, it becomes little more complex. That's why we'll separately we'll discuss. We'll bisect and we'll discuss separately. But yes, the point what you said is correct. Capacitor shorts are, we can consider as short circuit only at very high frequencies. Otherwise, yes, we have to consider the effect of capacitors also. My point here is to find different parameters. As I told you, you just need to have some method or shortcut to find, because I can't derive all these expressions at this point of time. I can't derive, but I can explain how you have to proceed. First thing you have to find is input impedance, right? Input impedance you have to find. So always guys, you have to see from here. This is how the input impedance seen from the input terminals. This is the input terminal, so you have to see into the input terminals and you see how to find it. When you are finding the input impedance, I am giving the shortcut. Okay, it can be derived. I am not deriving. I am giving these equations in terms of RE, assuming RE model is used. You can derive in the same way using H parameters also, RPi model also, whatever. So if you see from the input terminals, the base, right? You see from the base, whatever resistors are connected to the base, put them all in parallel. Okay. What are the resistors connected here to the base? Only RB. This is RB in fact. Okay. So put them in parallel. RB. Just a second. RB parallel. After this base resistance, what is there? Transistor is there. Between base and emitter, what is the resistance in the RE model? In common emitter, what is the resistance? If you go back and see RE model for common emitter, resistance is from the base. What is there? Beta RE is there. So that you have to put it here. Beta RE. Now RB is known, beta is known. RE we can find. RE is equal to what? 26 millivolts by IE only. We know how to find IE already. So find RE, substitute here, you will get the input impedance. Okay. The second thing what you want is AV, voltage gain. Second thing what you want is the voltage gain. Voltage gain is when you want to find the voltage gain. Again, I am not giving the derivation part. I am giving you directly the shortcut method or directly how to find the voltage gain. Okay. If you see common emitter amplifier, if you are writing the voltage gain for common emitter, first thing is you have to put a negative sign because there is a phase shift. First thing you have to put a negative sign. Second thing is, where is the output? Output is from the collector, right? You see what are all the resistors connected at the collector, put them all in parallel. What are all the resistors connected in the collector, put them parallel. What are connected to the collector? RC is connected. RL is also connected. Whether capacitors are there or not, doesn't matter. Okay. RC and RL are connected, so put them in parallel. Minus RC parallel RL, put them in parallel, divided by small re. Divided by small re. That's it. That is RE. That is AV. Okay. Now third thing is AI. AI for common emitter amplifier, whatever the biasing is, okay, is simply beta. Remember, it is beta. Yes, Ravi Shankar, it is fixed. At room temperature, if temperature is 300 Kelvin, it is fixed. At room temperature, it is 25.9 millivolts actually. We take it as 26 millivolts. AI is simply beta. And the fourth one is required is ZO, output impedance. Output impedance is seeing from the output terminals. Like input terminals, you are seeing the input resistance. Output resistance is seeing the output impedance. You see after the load, whatever you find the resistances in the collector, that's what output impedance. So what you find? Collector resistance is only RC, that is ZO. If you want including this RL, that is RL parallel with RC. That's it. Isn't it simple, guys? Isn't it simple? So any circuit you can do like this. Now let's see cell bias circuit. Analysis of CE amplifier with cell bias circuit. Again, I'm not going to tell you how the analysis, etc., etc. The first thing is you have to find Zi. What I told? Come on, guys, repeat. See from the input terminals. Input is at base. From the base, whatever resistors connected are in parallel. So at the base, what are the resistors connected? R1, R2. Put them in parallel. R1 parallel R2 parallel. After this base, this junction resistance is also there, na? What is that? Beta Re. Put them in parallel. Beta Re. That's it. That's the Zi. Of course, that can be derived. I am telling you, I am not deriving, but it can be derived. I am not doing it. Next one. What is wanted? AV. Okay. Common emitter amplifier. Simply put negative sign first. Done. Then collector resistances. Collector. Output is taken at collector. What are all the resistance connected? Collector resistance RC, load resistance RL. RE is not connected anywhere to the collector. Collector को connect नहीं हुआ. So we need not to consider RE there. So it is RC parallel RL divided by small re is as usual. Suppose if you have one more resistor connected here, let us say for example Rx, then comes in parallel Rx. That's it. Okay. So here for easy point of view I am removing it. So if it is there, you have to put there. Then third one is what? AI. What is AI? Beta. And the fourth one is what? ZO is what? RC. So directly you can say, but don't by heart them. Even you can by heart it also, but why to waste your memory? You just need to see how many are the collector resistors, put them in parallel. You just need to see how many are the base resistors, put them in parallel. Because different biasings will have different resistors. So need not to by heart anything. Just understand the method. Okay. This is about the CE amplifier. This is CE amplifier again, but this time it is without bypass capacitor. So there is no bypass capacitor. See, this capacitor what we connected here, this capacitor is called as bypass capacitor. So which bypasses the AC signal passing through RE actually. There is a story behind this which can be explained, but I am skipping it. It's called bypass capacitor. If this bypass capacitor is not connected, the voltage gain AV will be smaller actually, will reduce. Because if you remove this bypass capacitor, there exists a negative feedback here. If negative feedback is not to be applied, then we have to have the bypass capacitor. So it is called bypass because it bypasses the AC current, which bypasses the negative feedback. If you don't want negative feedback, then bypass capacitor has to be connected. So here in this circuit, bypass capacitor has been removed. That means there is a negative feedback here. There is a negative feedback. So I'll show you again in feedback amplifier. See, okay, there is negative feedback. Similarly, you can find, but of course the equations are slightly different here. I'm not giving this here. And this is C amplifier already done. This is CC amplifier. Okay. CC amplifier also similar, slightly different it is. First thing is you just need to find Zi. Okay. Zi is from here, you just need to see from here, but here is slightly different. Formula is not same as CE. Of course, it is the parallel combination of base resistances. So it is R1 parallel R2. Okay. After that, it is parallel to R1 parallel R2 parallel beta Re, which is the junction resistance, plus 1 plus beta into capital Re. Please remember this. There is a direct shortcut. I cannot say this, but why that is coming, I can tell you, because this resistor is there, no, and the current flowing here is IE, where IE is 1 plus beta times of IB, right? So that's why that 1 plus beta term is coming there. So beta Re is up to this, it is actually normal, like normal common emitter, but this extra term is because of common collector, as output is taken from the emitter. So that point extra, if you can remember, that is sufficient, I think. But remember, compared to CE amplifier, Zi is larger than CE amplifier. That's why CC amplifier will have large Zi than CE. Second, what is AV? AV is again, output is taken from here at the emitter. So put all the resistors in parallel. So it is Re parallel RL without negative sign, because it is not CE. Negative sign only comes to CE by small re. Okay. It is not exactly, approximately it is. Exactly, if you want beta also to be considered, you can take it as approximate value. So third one is AI. AI is 1 plus beta and ZO, and the fourth one is ZO. ZO is seeing resistance from here, it is Re parallel small re. So from this we can say output resistance of CC amplifier is lowest, because parallel combination of Re results almost equal to small re. Okay. So it is smallest, input resistance is highest. Moving to CB. What is CB? Input is at the emitter, output is at the collector, base is ground. That's what CB is. In the same way you can get these equations, guys. I'm not writing this. The same way you can do it. Like if you find input from here, etc., can be done. The CB is not that very important compared to CE or CC. CE and CC are more important. Remember that. So CE amplifier with collector to base bias is slightly different and very important. Please pay attention here. I want to spend some time here because it is frequently asked in the examination. Whenever you have this CE amplifier with collector to base bias, see, biasing method is collector to base bias used. If this is a circuit, you have to be little careful. Why? Because of this resistor. This resistor is between output, this is output terminal, and this is input. This is between output and input. So this resistor is between output and input, that provides some negative feedback. Sir, input loop for voltage gain RB must be in parallel to RE for input loop. Ishwanath, here you are asking? In which circuit? I didn't understand. CC or CE? Then I can tell you. So by the time I'll explain this, okay? So what you have to do is you have to apply Miller's theorem. Remember, when you have collector to base method, you have to apply Miller's theorem. Miller's theorem to the CE amplifier. So what this Miller's theorem tells you? So this is the BJT you have, and this is V2. Capacitor I am taking it as short circuit, okay, and base is input, of course, RS and VS, and C1 also I have taken short. This RC will be in parallel because we are shorting the DC. When this DC is shorted, RC is between collector and ground, Now this RB has to be replaced here at the input, please pay attention, and also here at the output. Okay, but you call it as Z1, you call it as Z2, where Z1 is RB by 1 minus AV, Z2 is RB by 1 minus 1 by AV. Like this, you have to replace Z1 and Z2. With Z1 and Z2, this RB has to be replaced like this. Then it looks like normal CE amplifier, where this Z1 and Z2 can be found by finding the AV value, where AV is what? AV, as I just told you, negative sign because it is CE, and you see from collector whatever all connected, Z2 and RC, they are in parallel, Z2 parallel RC by small re. Suppose if I want Zi, so what is Zi? You have to see from the base what are all connected, put them in parallel. Z1, yes, Z1 in parallel with what? Beta Re. Z1 is beta Re. Okay. I will break down our resistance. So CMOS capacitors, when it will be completed, CMOS capacitors, MOS capacitor, talk about MOS capacitor. CMOS is a circuit. MOS can be used as a capacitor. That we will cover in EDC part, guys. Sir, in CE input loop, sir, voltage gain input loop RB and RB. No. Vishwanath, if you see the RE model for CE, RE model for common emitter, this is not RB, it is RE only. It should be RE only. That is why it is called RE model. Every resistor, whether it is at base or at emitter, represented in terms of RE only. That's why it is called RE model. So we can't call it as again RB model. So there is only one model as RE model. Yeah, coming to this one. So this is very important, guys. This point you please note. Whenever you see CE amplifier with collector to base pair, you have to apply Miller's theorem and then proceed like this. Okay. Coming to the frequency response. This is what someone asked. So yes, definitely, as someone asked, I think Vishwanath or someone asked that how about frequency? So frequency response is the graph drawn between gain and frequency. So is the gain constant with respect to frequency or not? Is the parameter tells you. Definitely, as per the graph, if you see, it is not. So gain is falling at low frequencies and gain is highest to some range, and gain is again falling at high frequencies. So this range we call it as high frequencies, this range we call it as low frequencies, and this is mid frequencies we call it as. And remember, the fall in gain here is because of C1 and C2 coupling capacitors. We connected the coupling capacitors, that is the reason why gain falls at low frequencies. Why gain falls at high frequencies? Because of junction capacitances of the BJT. Okay, junction capacitance of the BJT is the reason why gain falls at high frequencies. Why gain falls at low frequencies? Because of the coupling capacitors what we connected. Coupling capacitors are, you know, the input capacitor, output capacitor, etc. The gain will be maximum at mid frequencies, and the value of F1 is called as lower cutoff frequency. F1 is called a lower cutoff frequency, at which the gain falls to 0.707 times of maximum gain. You see, this F1 is at this point. The frequency where gain falls to 0.707 is called lower cutoff frequency. The frequency where gain falls to lower than 0.707 times of AV max is also called as F2 at high frequencies. This is F2, and the difference between these two is called as bandwidth. So bandwidth of the amplifier is F2 minus F1. F2 minus F1. Done, guys? So this is about frequency response, and important concept when we talk about high frequencies especially, and also low frequencies. So it tells you that you have to operate your transistor within this F2 and F1. That is what we call it as bandwidth. Okay. Input impedance must be there na at denominator, फिर voltage gain. Why RE is only included in RE along with parallel combination must be at, in CC you are asking. In CE only beta RE is there, na? Beta RE is there, not only just RE. RB is there. In CE we have included. If you see, if you are talking about CE, see here, RB beta RE, it is there. Vishwanathan. So frequency response is done. Yeah, this is frequency response. These are some problems, guys. Yeah, then first we find ZI only, then AV only. Yes, that's correct. Yeah, these are some problems. Of course, I am skipping these problems. Please again take the screenshot of these problems, take the homework. Problems can be taken as homework. If you don't get it, then I'll get it. Acha, in the denominator you are asking. No. Actually, Vishwanathan, actually you will get it as 1 plus beta times of RC parallel RL divided by beta RE. You will get it like this with a negative sign, of course. AV, you will get it like this actually. 1 plus beta and beta will be almost same, na? So we will get cancelled. That is why it is AV almost equal to minus RC parallel RL divided by small RE. You will get like this. That is the reason why. Got it now? When you are deriving actually, you will get the equation like this. So you will get cancelled this 1 plus beta and beta. So you will remain with minus RC parallel and divided by small RE. RB, capital RB will not be included. No, because gain is voltage across capital RB and voltage between base and emitter are same. No, RB will not come because what is voltage gain? AV is output voltage divided by input voltage, na? Input voltage is nothing but voltage across RB or voltage across base and emitter. So we will go with base and emitter because we know how much is that. Voltage across RB is not known in terms of IB and others. So this is 100% right, no doubt about it. Okay. Yeah. Voltage gain of the circuit shown below here is. So you have to be very careful here, collector to base bias. So you have to apply Miller's here. You have to apply Miller's theorem here. Then only you have to find it. So these all you can take it as homework, guys. Please take it as homework, take the screenshots and finish it. Now feedback amplifiers. Okay, feedback amplifier is, the name tells you what is feedback amplifier. The name itself tells you what is feedback. The name itself tells you something is fed back to the input, right? Output is taken back to the input called as feedback amplifier. This can be of two types, positive feedback and negative feedback. Vishwanath, due to time constraint, I am not able to take. I'll take another session otherwise with all problems. Let me finish the revision part, and problems you can try with the formulas I have given. And as I told you, you can ask me in the mail if you need any guidance or any help. I can solve and I can revert back to you, or I'll plan another full session for only problems. Okay. So this network, what we are giving back is called as feedback network, and this amplifier is basic amplifier. For any amplifier, we can give a feedback. So based on how you are giving this, the feedback, how you are giving the feedback is of two types, positive feedback or negative feedback. If Xi is modified as Xs plus Xf, Xf is the signal what you are taking back. This is called positive feedback. If Xi is modified as Xs minus Xf, this is what we call it as negative feedback. And we talk about negative feedback only. Here in these amplifiers, we don't talk about positive feedback, because positive feedback is not used in amplifiers, or if you use positive feedback in amplifier, amplifier will not be no more as an amplifier. It may be called as oscillator, or it may be called as Smith trigger, it may be called as multivibrator, etc., etc. So positive feedback will not be in amplifiers. Positive feedback is for some other circuit, not as an amplifier. But negative feedback is in amplifiers and it still behaves as an amplifier, even you give the negative feedback. So what is negative feedback? Like this. This is very important. And what is the effect of negative feedback? This is very important. What happens if negative feedback is given? If negative feedback is given, gain reduces, gain will be lost. Distortion will be reduced. This is an advantage. In fact, this is a drawback. Okay. Lower cutoff frequency is reduced. Advantage. Higher cutoff frequency is increased. That means bandwidth increases. It is an advantage. Noise decreases. Yes, this is also an advantage. This is stabilization of gain happens. This is also advantage. So these are all the reasons why negative feedback is taken. So with the negative feedback, lot many advantages, but only this is the drawback where we lose gain, Chetan, great Chetan, thank you. Love from Pune. Thank you. Love from Delhi and Hyderabad. That's great. EDC also one of my favorite areas. I can make EDC very, very simple. Generally, people will find it is very difficult, but I can make it very easy. Yeah, great. So these are the effects of or result of negative feedback. Some positive, some negative. Mostly are positive. That's why we prefer to go for negative feedback in amplifiers. Okay. And then what are the types? Voltage series is one type, voltage shunt, current series, current shunt. This all depends on what you collect it as output signal and how you connect it at the input. Feedback is what? Taking something and giving back. What you take, how you mix, gives you four types of feedbacks. So one of them is voltage series. You see, this is the voltage you are taken and given at the input in series. This is why it is called voltage series. Voltage is taken and added in series. Voltage series it is. So important parameters here is what is ZIF. If feedback is given, how the ZI is modified and how the ZO is modified. Okay. So ZIF is modified as ZO into 1 plus A beta. So ZI with feedback increases in this type of feedback of negative feedback. Voltage series negative feedback results input impedance increased. How much? As per this. Output impedance is ZO divided by 1 plus A beta. So output impedance decreases. So it can be derived, of course, but I am not going to derive this. So just remember these equations is more than sufficient. So voltage series increases the input impedance and reduces the output impedance. So this is the one of the reasons why we go for negative feedback. If you want the ZI and ZO as per your requirement, you can go for this type of feedback. No, not like this. I want some other way. I want this also to be increased. I want this also to be increased. Then there is another type of feedback you can go for. So depending on how much is ZI and how much is ZO you want, you can go for different types of negative feedback like voltage series, voltage shunt, current series, current shunt, etc. Let's see the next one then. Voltage shunt, what it gives? See, voltage is taken, connected in shunt. So that's why it's called voltage shunt. So how this Zi is modified here? ZIF is equal to Zi divided by 1 plus A beta. So that means the voltage shunt negative feedback reduces the input impedance with the feedback. ZOF is also ZO by 1 plus A beta it is. So both voltage shunt negative feedback reduces both input impedance as well as output impedance from the basic amplifier. Basic amplifier Zi is this and ZO is this. With feedback they are modified like this. So they are both are decreased. Similarly, current series. See, you can say current is sampled and added in series. That's why it's called current series. Series addition is also called as voltage addition. Remember, series addition is also called as voltage addition. So ZIF here is equal to Zi into 1 plus A beta, and ZOF is ZO into 1 plus A beta. So where beta is called feedback factor, it is always less than 1. A is the gain of the amplifier, and Zi, ZO are input impedance and output impedance respectively. For better amplifier, we require input impedance is high and output impedance is low. Hemant, it depends. It depends on better amplification. Amplification means it can be through voltage or it can be through current, right? Now, what you want to amplify, voltage or current, depends on how you want this Zi and ZO. Based on Zi and ZO, voltage or current gets amplified. If you want more voltage amplification, then Zi should be large and ZO should be small. If you want more current amplification, Zi should be small and ZO should be large. It all depends. Okay, we can't generalize that. Yeah, this is current series. Okay, and the last one is current shunt. Current shunt. So current is sampled here, added in shunt here. See, shunt addition is nothing but parallel addition. Shunt addition is also nothing but current addition. Okay. So what is ZIF here? ZIF is Zi by 1 plus A beta. ZOF is ZO into 1 plus A beta. So these are Zi and ZIF. ZIF, ZOF, ZO. So these are very, very important. Please by heart this, or you just remember the way however you want. Okay. So these are some of the to identify the type of feedbacks. Now we have seen voltage series, current series, voltage shunt, current shunt, etc. So to identify what is the type of feedback, the first thing you need to do is, I'll tell you three simple methods, three simple points again to identify what type of feedback is. One is you identify the feedback resistor. Feedback resistor is nothing but common resistor between input and output. So in this circuit, RE is the common resistance between input and output, because this resistor belongs to only output, this belongs to only input. So this is the input and output common. Then identify the first point is identify the feedback resistor RE. Second is the output taken from the feedback resistor? If yes, it is voltage sample, otherwise current sampling. Is the output taken from the feedback resistor? No. Feedback resistor is here, output is taken somewhere. So that means sampling is current. Then the third question. Is the feedback resistor connected back to the input or not? If yes, it is current mixing or shunt mixing. No, series mixing. So is it connected back to the input? No. That means it is series mixing. So this is current series negative feedback amplifier. Only 3 questions. Okay, let me show you with another. This one. So what is the feedback resistor? RE. Here also this is common. RE is the feedback resistor. Is the first question. Second question. Is the output taken from the feedback resistor? Yes, output is taken from the feedback resistor. So that means it is voltage sampling. If not, current sampling. Now, is the feedback resistor connected back to the input? That is the third point. No. So it is series mixing. If yes, it is shunt mixing. Isn't it? Like this. So very simple it is. Let's see the next one. So what type of feedback again? This is the feedback resistor connected between output and input. See, this is between input and output. This is a feedback resistor. Right? Now, is the output taken from the feedback resistor? Yes. So it is voltage sampling. Is it connected back to the input? Yes. So it is shunt mixing. So it is voltage shunt. Isn't it simple, guys? These are all shortcuts. Go to the next one. So what is the feedback resistor here? So this is the feedback resistor. This is not, because this is not connected to the input. This is the input. This is not input. This is not input. But this is output. So this is not feedback resistor. This is the feedback resistor, because this is connected from here to here all the way. So feedback resistor is identified. Second question, is the output taken from this? No. So it is current sampling. Is it connected back to the input? Yes. Shunt, current shunt it is. So this technique can help you in identifying type of feedback. Isn't it good, guys? Yes or no? This helps us. Of course, formulas you can again go through. Formulas again I am skipping. Coming to the multi-stage amplifiers. The last topic, guys, another 10-15 minutes. Yes, another 10-15 minutes can finish this. Ready, guys? What is multi-stage? It tells, name tells 2 or more than 2 stages of amplifiers connected in cascade. Is called as multi-stage amplifiers. A transistor circuit containing more than 1 stage is called as multi-stage. 2 or more stages connected is called, like amplifier 1, output is connected to input, another 2. This is what multi-stage amplifier is. Now, why we go for multi-stage? There are multiple reasons why we go for. Sometimes we may go for multi-stage for gaining more and more voltage gain or current gain. Maybe sometimes for impedance matching, or maybe some special characteristics like Casco, Darlington are the reason why we go for some speciality to get, not for gain. Hemant, not only gain, multi-stage is for different reasons. Sometimes maybe impedance matching also. So you now understood what is multi-stage, why multi-stage, then how multi-stage can be done, how to connect different stages. There are different methods, types of coupling we call it as, different methods to connect one stage to other stage. It's called RC coupling, transformer coupling and direct coupling. So this is RC coupling, where using capacitors, one stage to other stage are connected using capacitor. This is called RC coupling. Using transformers, called as transformer coupling, like this. One stage to other stage are connected. Different methods are used at different applications. Sometimes maybe it is required direct coupling, or sometimes transformer coupling. It all depends on what type of amplifiers and what you want ultimately. Depends on application it is. Okay. And then direct coupling without any transformer or resistor, direct coupling. But direct coupling is on very special cases. Not on every amplifier direct coupling can be used, because that violates the biasing conditions. So you have to be very careful while using the direct coupling. It cannot be used in every amplifier. There are special amplifiers which are at very low frequency and very low gain. That type of amplifiers are called as direct coupling can be done. Then what is the effect of voltage gain on having multi-stage? If amplifiers are cascaded like this, this is amplifier 1, this is amplifier 2, then what happens to the overall gain? This is a very important point, is overall gain gets multiplied. So overall gain is equal to voltage gain of 1 into voltage gain of 2 gets multiplied. That is the reason why we go for multi-stage. Suppose there are 3 amplifiers connected, overall gain is product of 3 individual gains, right? Similarly, current gain also gets multiplied. AI, overall current gain is AI1 into AI2 into AI3, etc, etc, etc. If you have 5 amplifiers connected, overall current gain gets multiplied. That's why a large gain is possible. Okay. So this is the summary of the points I said about voltage gain and current gain. This is ideally product of voltage gains, individual voltage gains, overall gain. But practically input resistance, output resistance also plays a role. So practically this should be the formula. So practically it is not just product of individual voltage gain, it is slightly lesser than that. Okay, slightly lesser than that because of Zi and Zo. Similarly, current gain ideally should be this, but practically including Zo and RL, Zo and Zi should be like this. So please be aware, it all depends on in the question, if it is said practical or ideal, as per that you have to use this formula, not always just product. Okay, this is about multi-stage. And cutoff frequency, as you know, this is the frequency response, right? This what we call it as F1, this what we call it as F2, and this is what 0.707 times of AV max, and this is F1 and F2, lower cutoff frequency, right? This is AV max. Okay, but if multi-stage is done, gain increases, we know. So the gain increases like this, but the bandwidth decreases. Gain increase, AV max is increase, but 0.707 times is this. So this one is F1 now, this one is F2 now. Similarly, if I go for negative feedback now, this will reduce the gain, but F1 is decrease and F2 is increase. So bandwidth increases. Negative feedback increases the bandwidth, reduces the gain. Multi-stage increases the gain but reduces the bandwidth. So that's what here it is said. How to find lower cutoff frequency of nth stage of amplifier? Nth stage, n indicates number of stages. FL divided by 2 power 1 by n minus 1, and FH is like this. So if number of stages are 3, n is equal to 3. If number of stages are 10, n equal to 10. If number of stages is 1, n is equal to 1. Okay. So this formula you have to remember. So these are all different possibilities of two-stage amplifier: CB, CB, CE, CB, CC, CC. Out of this, CE, CB is important and CC, CC is important. This is called cascode and this is called Darlington. These are special multi-stage amplifiers which can be understood from this. This is what cascode is. Okay. This is what cascode amplifier. The input is here, output is taken here, that is given to the emitter and output is taken at collector. So this is common base and this is common emitter. CE-CB combination is called as cascode amplifier. CE-CB combination is cascode. CE-CB is cascode. Why cascode amplifier is required? It has higher bandwidth. Bandwidth is higher than the single stage amplifier. Overall voltage gain is equal to the single CE stage amplifier. That means we are not going for this cascode for gain because it is equal to the single CE amplifier. So you are not getting additional gain. But why you are getting? What you are getting? Larger bandwidth than the single CE amplifier because of higher frequency junction fall. The fall in higher frequency gain is because of the junction capacitances. That effect can be reduced using the cascode amplifier. That is why we go for this. Okay. So why we take these combinations are different combinations for different applications. As I told you, some combination is for gain, some combination is for impedance matching, some combination is for bandwidth, some combination is for input impedance, etc., etc. Different combinations will give different applications. So here you will get higher input impedance than the single stage CE amplifier. Overall transconductance of this cascode amplifier is equal to GM1 because that means it behaves almost like CE amplifier, but higher frequency bandwidth is larger than single CE amplifier. That is the reason why we go for it. Similarly, Darlington pair. Darlington pair is nothing but CC-CC. So input is here, output is emitter. That emitter is given again to the base and output is again taken at emitter. That means this is common collector and this is also common collector. This is a common DC supply biasing for both. So this is what called as CC-CC. CC-CC called as Darlington pair. And remember, it is always available as a pair in the form of IC. You can't connect two transistors like this and try to use it as Darlington pair not possible. This combination is fabricated in the form of IC and is available in the market, which gives you advantages, which gives you larger input impedance, much higher input impedance, almost equal to beta 1 into beta 2 into RE, or beta square RE almost equal to, where beta itself is large, around 100 it is, beta square is much larger, RE is multiplied with that. So it's very large input impedance it can provide. So why we go for Darlington pair is, one of the reasons is very high input impedance, and the most important, another very important point is large current gain, which is equal to almost beta square. Large current gain is also possible using Darlington pair. So these are the reasons why we go for Darlington. This Darlington and this cascode are very important, guys. If at all any question comes from multistage, must be from these two. Okay. So these are some questions from multistage as well. That's it, guys. Finally, with 5 hours, I have taken extra 1 hour 6 minutes, but still I am able to complete this. So GATE and ESC students, if you are after this revision is over, you want to practice mock test, then unlimited access to full-length mock tests, subject-wise tests, link in the description in the channel, you can check it. You can practice these questions as well. Okay, these are all the features available in the app and with the BYJU'S. Don't forget to subscribe, share and like. That's all for today, guys. I summarize diode circuits, BJT biasing and amplifiers, feedback amplifiers, multi-stage amplifiers to the best of my possibility within these 5 hours. Thank you all for staying with me and learning something with me and supporting and replying to me. Hope this is helpful for you, and if it can give you extra 2 marks, extra 5 marks, extra 1 mark, that's all, the purpose is survived. Thank you all, guys. Thanks for your support. All the very best, guys. Thank you. Thank you, guys.